I now request Director NIT Goa to provide a floral welcome to Professor G. Narayanan. I now request the Director to kindly address the audience.
Namaskar, a very good morning. Professor Narayanan, Mrs. Narayanan, my faculty colleagues, dear participants, students, ladies and gentlemen. On behalf of NIT Goa, I welcome you all for this program. Since Professor Narayanan is with us for the last 3 days, apart from academics, I will request all the participants to learn, so to say, good academic practices or how flexibility in academics is being used to nurture the students. Okay. Professor Narayanan is from ISC Bangalore, one of the best institute in our country. Whatever practices they follow, so during lunch break and during other places, whatever discussions you will have, I am looking forward to more extract from those things. Okay. That you'll take care of. That I am sure. So I need not tell that. I know. See, in academics, okay, means since we are dealing with students, okay, we are nurturing them. Apart from they becoming a good in their domain, okay, how can we make them good human beings? Okay, how can we make them more accommodative? Okay, as a academician, as a researcher, as a teacher, okay, qualities are very much required. Has Professor Gadre joined us? Yes. Yeah. Professor Gadre, welcome.
Good morning. Can you hear me?
I am Jaiswal, Director NIT Goa.
Yes.
Professor Gadre, Professor Narayan is with us.
Yes.
You can come here. Yes, I think they are focused here.
So, good morning, Professor Narayan, and thank you so much for, conducting this workshop under ANRF PAIR.
Sure. Thank you so much. It's a pleasure. You might recall our meetings during our sadhana.
Yes. That's what I remember, So that's why I saw your name.
Yeah.
Suddenly struck a bell. So I'm so grateful that you've, agreed to come and join us and, conduct almost all the workshop. So it'll be a very valuable resource that we create with your, lectures.
Thank you, sir. Thank you so much.
Nice. So we just started, Professor Gadre. I was just telling students and our faculty colleagues that we should take maximum advantage of Professor Narayanan's presence here. Okay?
Yes.
Not only in terms of academic delivery, which he will do, but otherwise also. He's a very good teacher back home at ISC Bangalore. Okay.
Yes.
So whatever flexible approaches they follow there, okay, good practices they follow there. How can we make best use of them? Okay.
Yeah.
To nurture our students here, to nurture our faculty members over here. I did my PhD from ISC Bangalore. So if somebody asks me, what do you recollect best from ISC? Once I heard Khushwant Singh there. Once I heard Hari Prasad Chaurasia there. Once Arun Shourie ji had come. Okay. And so many Nobel laureates. They keep coming and delivering lectures there. Whatever those events had effect on individuals shaping that time. That is what that governs, isn't it?
Yes.
So NIT Goa is a new institute. Okay.
Yeah.
We are hardly now 10, 12-year-old, and it is 2 years since we shifted to this campus. Whatever culture all of us together will lay down now. will decide the destiny of this institute. Okay, the future that will remain like that, isn't it? One institute from other institute differs only in terms of that. Okay, Newton's second law of motion is being taught everywhere, be it a government engineering college, a state government engineering college, or be it IIT, be it ISC. Okay, but what differs, okay, and what matters, okay, is the ecosystem there, the culture there. As they say, no, means if you see at MIT, Harvard, and or a cup of coffee, maybe they will be discussing the Nobel Prize awarded that year. Whereas in a coffee shop in other institutes, topic of discussion will be something else. Okay, those things immensely matter. Okay, and that is where having interaction, no, and that is where I appreciate our ANRF team also, that they chose to call Professor Narayan here, have him is here with us for 3 days. Okay, and so that we can imbibe these informal discussions, a lot of things from him, and we should encourage more and more of such things. Let senior faculties, senior experienced people from other fields also come talk to us. Many of us should go to other places also. Okay, so in academics, this type of interaction is very important. Okay, it accelerates our shaping, it accelerates the way we bring the culture in our institute. Okay, so from that point of view, this 3 days, I'm sure, will be very much productive, helpful, and resourceful to all of us. Okay, I thank Professor Gadre. Okay, ANRF had been a big this thing for us. Okay, we are trying to make use of whatever funds have been made use of to hire good resources here, good manpower here. Okay, and I think machines will come in due course of time. IIT Bombay is helping us. Okay, and one good thing ANRF has done is that it has tried to reduce the purchase headache from the spokes. So that is good, because all said and done, we are more rigid in purchases and other things as compared to IITs and ISC. So that is the big advantage. So that our team here did not spend much time on that. Otherwise, comparatively, we are more frustrated lot. As far as interaction with account section is concerned, establishment is concerned. Okay, so means, and being new now, we don't know what to do, what not to do. Okay, but nevertheless, whatever proposals are coming from my colleagues, okay, we are taking them to BOG. We are trying to see that as much flexibility we can provide to them. Okay, we have CPDA, in which in 3 years you can spend 3 lakh rupees. So there is a rigid rule that 1 lakh per year. So if some faculty has to go abroad in the first year, then he will get only 1 lakh, or rather 70,000 only. Then I told BOG, no, this won't help. Okay, so allow them to use that money also. You can reimburse it after 6 months when new academic year, new financial year starts. Okay, so only it is matter that good proposal should come. Okay, otherwise the required flexibility is available in NIT system also. So we will try to implement that also. Okay, and whatever good practices we follow, my colleagues will see after this 3 days interaction. If some good proposals come, again we will take back to our statutory bodies and see that we get as much flexibility as possible. Okay, so with these initial words, okay, I wish all the best to all the participants. Okay, and I am very much thankful to Professor Narayanan for coming here and spending 3 days with us. Thank you, Professor Gadre. Thank you very much. I hope ANRF will continue to yield good fruits for NIT Goa. Thank you very much.
Thanks a lot, sir. I warmly welcome Professor V.M. Gadreji from IIT Bombay, who is also the project director of IIT Bombay NIT Goa ANRF pair project, and also the chief guest of this function. And I request Professor Gadre to kindly address the audience.
So a very good morning to the entire audience. Am I clearly visible and audible, Professor Suresh?
Yes, sir, audible, sir.
Yeah. So it is my privilege to address you, albeit online today, and particularly, to see that NIT Goa is taking these initiatives to organize these events under ANRF pair. My role in this inaugural function is to tell all the participants a little bit about ANRF pair. PAIR is an abbreviation for Partnership for Accelerated Innovations and Research, PAIR. ANRF, I think, is very well known to all of us. Anusandhan National Research Foundation. PAIR is a very important initiative which has been taken up by ANRF. The objective is to have, the so-called hub institutions. In this case, IIT Bombay happens to be the hub institution, to collaborate with the so-called spoke institutions. And NIT Goa happens to be one of the 7 spoke institutions associated with IIT Bombay as a hub. The aim here is to partner, as the name suggests, partner in accelerating both innovation and research. Now, when we say innovation may also lead to, for example, entrepreneurial endeavors. It may lead to even innovations in the way people do research, development, or carry out translational efforts, and so on. Research, of course, research and development, we all understand. It's not, these are familiar terms to us. But, the whole objective of PAIR is to ensure that all the, as your director said, all the good practices of both institutions are shared. I mean, the hub and the spoke institutions. They are shared to form a more vast and a better spread ecosystem where research and development flourish and grow by collaboration, by working together, by doing things together, by finding common interests, by finding common strengths, and so on. In that context, we are very happy that NIT Goa has taken it upon itself to organize this workshop with a very reputed faculty member from the Indian Institute of Science, Bangalore, namely Professor Narayanan. I'm also very grateful to Professor Narayanan for having agreed to deliver quite a bit. I was looking at the schedule and I realized that he's really delivering quite a bit of the program, almost the whole program. And believe me, that's not easy to do. It really requires a lot of stamina. It requires a lot of grit and gumption. And Professor Narayanan is more than equal to it, I know. But we must particularly place on record our gratitude and appreciation to him for having agreed to put in that kind of energy and that kind of dedication and that kind of effort in conducting this workshop, which is critical to the specific topic on which the workshop is based. It's a very important topic today. And I'm glad that Professor Suresh and his colleagues are organizing a workshop based on that topic. There is a lot of research and development which can go around the theme of this workshop. And I'm sure the interaction of all the participants with Professor Narayanan will ensure that you find certain new avenues for exploration, for innovation, for translation. It's my passion to talk about Atmanirbhar Bharat. Our Honorable Prime Minister has very rightly said that in these difficult times in the world, our country must shine by being self-reliant, by being knowledgeable, by growing with knowledge as an important component of its economy. And ANRF PAIR is one vehicle to do so. So, through this workshop, not only must you gain the, what you may call traditional knowledge that is associated with the theme of the workshop, but you must also gain an insight into how you can make our country self-reliant through these partnerships that we have between hub and spokes. Participants participate very enthusiastically even after this work. Making Atmanirbhar Bharat, Vikasit Bharat, Vikasit Maharashtra a success. Vikasit Maharashtra, Vikasit Goa. See Goa as a state think of Vikasit state in which we are. Many of you would come from many different at the state level and our country Vikasit at the national level. And ANRF pair should be a vehicle to do that. Finally, but not the least, it is very important that you carry away from this workshop not simply the tenets and principles of the theme of the workshop. I'm talking about the director NIT Goa very beautifully said in his opening remarks. What matters is the culture of an institution. I'm actually privileged to have been associated with NIT Goa about more than 6 years ago on the board. So I've seen NIT Goa grow at close quarters. I have seen NIT Goa grow over almost 6 years. Believe me, you are privileged to be in a new NIT which has grown by leaps and bounds. I know many of the faculty members who are organizing this workshop, not simply as faculty associated with ANRF pair, but as faculty who have contributed to the growth of NIT Goa even in those earlier days when I saw NIT Goa at close quarters. So, when you attend this workshop, take with you also the beautiful qualities of this institution, NIT Goa, which has enabled it to grow from a fledgling NIT into an NIT of repute, an NIT which has a lot of success in its path to see. I would like to make an announcement as I conclude. We are of course going to roll out the research projects under ANRF pair. That is, already there in the proposal, and we are doing it, and all that you're doing is a part of that. But there is one more thing we are going to do, and I'm inviting all the participants also to associate with NIT Goa in that direction. Our Honorable Director, IIT Bombay, has constituted a committee which will be revising our curriculum and looking at the academic structure, revisiting the academic structure to look at several things, not just courses and credits and so on. Also, how we can engage our students better, how we can inculcate better values in students, how we can help them achieve their potential, how we can change the assessment systems, and all this has an impact on research and development. We would be involving our spokes in this process, and we invite all of you also to participate. Without further ado, and once again expressing my sincere gratitude to Professor Suresh Mikili and his colleagues for having organized this workshop, I conclude this little address for which I've been given this opportunity, and request the organizers to record all the proceedings of this workshop on YouTube, on videos, that we can keep it to posterity as a resource. Thank you so much.
Thanks a lot, Professor Gadre sir, for your valuable words and encouragement. As you have suggested, we are live streaming this entire 3-day workshop on our YouTube channel, and it will be a recorded thing as well. Thank you, sir. I now request Professor G. Narayanan sir to kindly address the audience.
So good morning, everyone. I'm very happy to be here. So I think, we were here last December during the STPAC. Yeah, I hope you're able to hear me now. I think, yeah. So I'm very happy to be here. So thankful to the IEEE department, to the director and the ANRF pair program for having me here. So anyway, I'm going to be talking too long. So for 3 days. So I don't want to be talking for too long now, right? All that I want to say is what is the goal of education, right? There are many. There's a question, right? What is the goal of education? What is that you want to achieve, right? So many people have asked this question. This question is a repeated question. It's an important question, right? There are many answers also, but I would like to say only 2 answers. I would like to say only two answers. One is a kind of a, what is a spiritual answer? The end of education is character. That is what all the great people over the ages have said. If you read Swami Vivekananda, what he says is the end of education is character. Okay, that's the goal. That is one of the goals. And think about it at a more lower level, like school, colleges, universities, right? Our academic business, and I think Professor uses the term academia also quite commonly. So, what is the goal? If I have to put that very simply, we are here to learn what? Learn how to learn. We are here to learn how to learn. Electrical engineering is just one case study. You pick up electrical engineering and you say, oh, this is a fundamental, this is a basic premise, this is what I do, that is what I do, right? And go and learn that. You can take economics as a subject and you can go about learning them. So these are all examples. Mathematics. These examples teach you. The goal is not to learn mathematics, not only to learn mathematics, not only to learn circuit theory, not only to learn fluid dynamics, but the goal is to learn how to learn. That's what I would say is the two things. For the question, like, what is the end of education? What do you get? One is, education should result in good character. That's one. And that's at a very evolved level. And at a more basic level, what we are doing is we are learning how to learn. So these are, I would say, would suffice as the answers in the entire spectrum of answers. So that's what we'll do. So today, what we'll do is we'll take power electronics as an example. And we'll see how to do that. And you can see there's electronics there. So we'll start with what is electronics, right? And what do you mean by power electronics? And that has power devices and converters. We look at it in an expanded form. It has not only power devices connected together, it also has magnetic components. So we'll look at magnetics. And magnetics is inductors and transformers. So they are static. But there are also dynamic ones, there are active ones. So let's look at machines, correct? And when you have machines, let's see how to control machines using power electronic converters. And then you can see that whatever you can understand by how to control machines using power converters, we'll converter control itself using that, right? So we'll go step by step into that. So that is what we'll be doing. So it's a range of activities. So we'll do about power devices and power converters, about magnetics, and then about electrical machines. And how do you control electrical machines using power converters? And how do you, in general, control power electronic converters, right? That's how what would be like. So all these are meant to teach us at the first level, these topics. And at the next level, in general, how to learn, no matter what you pick up. So that's what I would like to say. Thank you very much for the opportunity. So the only two requests I actually had was there should be interested people and their time. Those are the only two things. And my only third requirement was, of course, we need a classroom and a room to stay. And excellent arrangements have been made by NIT Trichy. And everything else is, superfluous and little too much. But I think, we do have the first two things, right? We have interested people and we have their time. So that's the most important ones. So let's see what we can do. Okay, it's to learn. Learn is an internal process. Please understand that. It's not an external one. It's not like somebody giving you a haircut. It's an internal process. We have to learn. And teaching is only, in some sense, aid learning. That's what I would put that. So thank you very much for this opportunity. I'll talk to you for the next 3 days. Thank you. And I also want to hear you for the next 3 days. Thank you.
Thanks a lot, sir. I request Dr. Suresh Mikli to propose the vote of thanks.
Respected chief guest of today's function, Professor V.M. Gadre sir, and esteemed director, Professor O.R. Jeshwar, and our distinguished speaker, Professor G. Narayanan sir, our today's organizing committee, faculty members, as well as dignitaries of the dais, students, participants, ladies and gentlemen. So I take this opportunity, or I'm considering as a privilege to propose the vote of thanks on the occasion of inaugural session of 3 days workshop on teaching learning process, or teaching learning workshop on power electronics, machines and drives. Okay, so at the outset, first and foremost, I would like to thank our ANRF project director and today's chief guest, Professor V.M. Gadre sir, for gracing this occasion with his presence, as well as He has explained exclusively about what is an ANRF pair and what the activities we are going to do there and what is the outcome about ANRF pair. Thank you, sir, for being with us and encouraging our students with your kind words. Thank you very much, sir, for your time and sharing your valuable thoughts with us. And next, when it comes to our institute, I would like to thank the director of NIT Goa for constant support and encouragement and presiding over the function. Thank you, sir. And I would like to thank Professor Narayanan, sir. Even though he was very busy, but he has given his consent to be here for 3 days with us. Entire almost all the sessions he is going to take from basics till the higher level. So thank you so much, sir, for sparing your valuable time with us. And thank you so much for giving your intro. And with this, I would like to thank all the organizing committee, as well as all the volunteers, even faculty, staff of EEE department, as well as other departments, and the PI of the program, Chirag, as well as other co-PAs of the ANRF projects, and all the volunteers and each and everyone. So because of you people, today we are going to have this inaugural session. Thank you for your contributions. Not only this, even all the events, getting the support from you people, all the BTech students, even MTech and PhD students, even faculty staff. We are like a family, we are going. I need same support from you. Thank you, one and all. And I would like to thank all the participants who are joined, even online as well as offline. Thank you, one and all. Your active participation makes it more successful. It's not just one lecture what the professor is coming and giving. How much you are taking from you or from the professor, how much you are taking, matters a lot. You have to spread. Here, ANRF project mainly bridging the gap between the institutes. So what culture they are following in IITs, they have to bring it to the NITs as well as central universities and private universities. So this workshop is meant for that. Here we want to bridge the gap between well-established IITs, IIScs, and well-established organizations to the central universities, other institutes. So we are putting our efforts. At the end of the day, how much you will take from this workshop, it matters a lot. Then only we can say like we will success. Okay. With this, I will conclude my vote of thanks and wishing you all the best for active participation. And I hope you will learn something and you should take something back to your home. Thank you.
Thanks a lot, Dr. Suresh. It's just to tell that totally we have got 45 registrations from external institution and NIT Goa, PhD, UG, PG together about and faculty together 130. So totally it's about 150 audience online and offline. So with this, I would like to conclude, thank all of them and conclude this inaugural session. Thanks a lot. Yeah, now all of you are requested to proceed for high tea, that is at the foyer, at the entrance of the EEE department. And assemble back exactly at 9:55. Session starts at 10 a.m. Thank you. Thank you.
name of this. So, okay, little far. All right. Okay. Yes, I will. Yeah, so I'll press and I'll erase this. So I'll have long press and then then okay. 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 Oh, oh, this is better. Ah. So, am I doing any mistake in holding it? Ah. Okay. Okay. Very good. Thank you. So let's start with that. So we have to break. See, there are different schools of thought, right? And there are different ways of teaching, whatever, right? Many. And as technology, there are so many things, right? The extremes end is saying that don't teach any student, teach an AI tool. Okay, so AI tool. There are professors who seriously teach AI tools. This also happens, and then they see what the AI tool does better and all that kind of stuff. That also happens there. So some people, in between, sometime about 20 years back, we came up with these slides and all that. So many people use slides, and some people don't, and some people use slides for something, and some people don't use slides for certain things. So I am also one of those. So one of the things about slide is good thing is it makes things fast. I just project. I don't have to do. There is no waste of time, perceived waste of time, and you can go on doing this now. But the other thing is the content, the entire content that is there in the slide cannot be absorbed by you at the same instant. Cannot be absorbed by you at the same instant, right? There may be water flowing like Ganga, but I want to drink water. What do? I open the bottle and I pour into it at a controlled rate. I pour into it at a controlled rate, the rate at which I can manage. If it comes from a big hose pipe, can I drink water? Right? If it is only controlled, I can drink. So sometimes when we write like that, that is to control the rate. So when we write, you follow what is being written, right? That is one. And not only that you are following, all of us are in sync at the time. If I'm writing a word called teaching, all of us are supposedly, okay, minds may be straying away something, assuming that all of us are focused, right? We are in sync with that. So that is also one more reason. This particular session, you can see I'm not carrying anything. I don't have any sheets, I don't have any pointers, I don't have something, and no slides. I'm going to only be doing this. This is again an experiment. Let us see what happens. Okay. Is everything all right? Very good. Yeah. So the first thing I read was teaching learning there. Correct? So morning itself, when I had a brief, occasion to talk, I just said learning, right? So what we say learn, said the goal that we have is to learn how to learn. That is the goal of education. That's what I said. So here we'll try to learn. We'll try to take power electronics as an example and we'll learn. So that is what we're going to say there, right? And there is a term called teaching also. So let me clarify for this purpose. See, there are always, do not think that a word has a very specific meaning all the time. Please do not think any word has a very specific meaning at all the time. Can you come up with some words which has same word having two different meanings? Can you try? No. You are saying N-O, K-N-O-W, the same pronunciation. The same word itself having two different meanings? Huh? Huh? L-E-A-D, the pronunciation, there is a small, this thing, you lead, right? And lead is a metal. Anything else? Huh? S-I-T, sit. Huh? Is seed, okay? Huh? Huh? Right, W-R-I-T, right, R-A-G-H-T, right. They appear the same to your ears, but they are different words. Over, completed. Game is over. Right? Very good point. It is going over my head. This professor is something that goes over my head. Both are over. Different. Correct? Any other example? Correct. They same pronunciation, but the words are different. But what he said is the word itself is same, but the meanings are different. It's just that you're not able to come up with now. There are many things where sometimes, let's say, the noun and the verb also may be similar. There's a noun form, L-O-O-K. What is that? Look. Is that a verb or a noun? Is that a verb or a noun? Verb, when I'm saying I'm looking at Sriraj. I'm looking at Sriraj, it is a verb. Here it means I'm seeing with my eyes. I'm looking into the design of power converter. Again a verb. I'm looking into the design of power converter means I'm examining, I'm investigating. That's also a verb, but that has a different meaning. Is look not a noun? Look at Sachin Tendulkar's look, man. That's appearance. It's a noun. Okay, so the word need not have the same meaning. There are words like that. If you take any typical word, in fact, you open the dictionary, any random word, the dictionary will give you several meanings. 3-4 meanings at the minimum, 8 to 10 meanings maximum. It will go on. Paragraph meanings will be there. 1, 2, 3. They will write so many meanings are there. Correct? So that is about every word. And other level, we define some words. Okay. And we will take it to understand something. You understand my point? Let's say we will call this something. I can give a name. I have a new control method. I don't know what to name it. I'll say let's call it ABC control. Right? I have a new power converter. Assuming that I have new power converter, I want to name. I'll say PQR converter. Okay, that is another extreme. Names get created. That's why if you look modern literature, read, right? So many new terminologies will be there, but you have to understand them. And sometimes names are there, right? The same thing, dictionary will give you this long meaning. Have you heard the term called encyclopedia? Right? Encyclopedia will be even more. They will give very detailed meaning. If you ask what is Karnataka, encyclopedia will give you big meaning of what is Karnataka. If you say Maharashtra, it will give you a very big meaning, right? That's not what it is. If you ask me Goa, I'll say Goa is a place. That's a state in India. Okay, that's what I will say. But then they can be very big. So I'm not talking of those meanings. I'm talking of at least simple meaning. We should have a working definition. So let's call that as working definition that all of us will understand that by then. So here, learning is what we are going to be doing. We'll do it all the time. There is a term called teaching. So what do we consider teaching here? Let me define it as teaching is simply helping someone to learn. Teaching is something like helping someone to learn. Does it sound like a reasonable meaning? Right? Aiding somebody's learning. That's all. So that basically means that is also learning. You need to know how to learn. I can't teach you how to make idli unless I know how to make idli. I can't tell you how to make tandoor roti unless I know how to make tandoor roti. Clear? So we need to do that. So that's the teaching learning part of it. And this teaching stroke learning is an adjective to the noun called workshop. So what do you mean by workshop? Place where work gets done. Place where work gets done. That's why you all had sandwich sometime back. That's why you had tea. Maybe you'll have a tea another 1 hour later too. Vaijayanti madam has arranged for that. Right? Why? Why? You have to work. You have to work. Don't think this is a shop where they sell something. Right? It's not that not that kind of a shop. But it's a place where you do work. So this is now a place where you're going to be doing working for all the 3 days. Okay. Work is towards what? Work is towards how to learn. Okay. How to learn what? How to learn what? How to learn? And what is power electronics? Everywhere we should have a working definition. What is power electronics? It's a subject. Correct? If you are in 3rd year BTech, you cannot say what is. I don't know what is power electronics. Yes? You are in 3rd year BTech? Huh? Can you say I don't know power electronics? Teachers are here. They'll get upset with you. Or they'll get upset with themselves. See this boy, this class I taught so much, Finally, they are saying I don't know what is power electronics. Yeah? What is power electronics? What do you mean by power electronics? There is a technique that we have learned from our ancestors. Don't take this wrong. Right? Not the ancestor as in your grandfather's grandfather, but we are Homo sapiens. We evolved from some other species. Right? If you take that ancestry, it has one habit. You know what I'm talking of? What is it I'm talking of? Huh? No. Our ancestor. Which ancestor am I referring to? Huh? Ape. Before ape. Whom you can very frequently see in trees. Monkey. Correct? They have one trait. Okay? I'm not very comfortable with this man. So what will I do? I will not see him. No. Turn this side. Why? I'm not comfortable with this man. That is a monkey's first response. When you go near a monkey feels uncomfortable with you. You are trying to threaten to something. Monkey will avoid seeing you. He'll pretend to do everything other than seeing you. This technique is beautifully adapted by some of our students in class. They say evolution. Some things change and some things don't change in evolution. There's a question now. So what do? I look at the maximum deviation from the line of sight. My antenna tracks that. Teaching technique. Line of sight. This gentleman is seeing me. Okay. That fellow is not seeing. Then he realizes. Or you call him. Okay. This trait we have not skipped. What your grandfather taught you have forgotten. But this trait of that, we have not done that. So don't do that in the class. Don't do that in the class. If you don't know something, say you don't know. That is what learning is about. That's what we are getting into now. Okay. Initial few minutes will be like this, light and philosophical before we get in that. But now we are into a technical subject. What is power electronics? In your considered definite view, what is power electronics? No answer is an incorrect answer here. Please understand. I will also tell you why that is not incorrect. Okay. Yeah. That obsession manner. He is obsessed. Let us say with power electronics now. So what is power electronics? I will repeat that. Okay, he says it is low current into high current, AC into DC, right? He says some conversion. But every term that he has talked about is something electrical. So he's talking of electrical power, maybe handling something. Anybody else? Control power flow. Okay. Light blue shirt. What is power electronics? So let's not deviate. See, the answer could be incorrect, right? No answer is perfect in such questions. But don't deviate. Don't go out of scope. You understand? Don't bring so many terms that are unconnected. Then, Sriraj asked me a question. I have to answer. Or I have to at least say, I know this part, I don't know this part. But if I go on diffusing, I talk about them and what Kishore Chatterjee did and what someone else did and what Trump is doing, you're not going to head anywhere. So stay focused on this. Don't deviate from the scope unless it is necessary to deviate from that. Okay. Yeah, try what is power electronics. Everybody should know because you have all done power electronics courses, right? What is power electronics in your view? To deal with the converters. Then the question will be, what do you mean by converter? They are examples of converters. Once again, the DC-DC converter, DC-AC converter, you are using the same term I questioned about. You ask me, you get my point. I'm asking what is power electronics. It's correct, a reasonable answer to say it deals with power converters. Correct. But that is assuming we have defined what is power converter. No, we have not defined what is power converter. Then I ask what is power converter. He says DC-DC power converter, AC-DC power converter. These are examples of power converter. Examples can make you think, certainly. Okay, it's not inappropriate, but still it is not a definition. Okay, let's try. What do you mean by power electronics? Okay, he is imagining some power supply. Okay, some source of electrical energy. Sit down, Kanna. Thank you. Some source of electrical energy. So that, it has some voltage, it has some frequency. And he thinks, I want some other voltage, some other frequency. How do I get that? Okay, power electronics is one way of getting it. Madam, would you like to try? What is power electronics? You are the only man. Okay, she gives more technical thing because she's been doing that. So she says, using electronics. Okay, you are trying to control power, control electrical power. She says control, convert, conditioning, many such terms are used. Okay, this you will find in some places. Okay, I'm not owning this, I'm just quoting this to you. Use of semiconductors, use of electronics to control, okay, power. Power is in the electrical form. Okay, they use the terms control, they use the term convert, and then they use the term condition. They use the three terms control, convert, condition, electrical power using electronic switches. Okay, there again, what is electronics? Still question repeats. Okay, there are two things, power and electronics, right? So here again, I'll tell you, power. What is power? What is power? Rate of change of, yes, rate at which work is done, rate at which energy is changed from one form to another form. But that is because you're sitting in a college, you're in a university now. If you're outside, what is power? Man walks in, everybody gets up. This way. That is power. Right? Yes or no? That is also power. See, very different connotations. Very different connotations. What are the seats of power in India? As per law, as per our constitution and governments. What are the seats of power in the country? Huh? 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 Yeah, there are three wings. Okay, one is judiciary, legislature, and this thing. Huh? Yes, executive. And all said and done, judiciary can only advise. The police, they can only tell the police, go arrest him. Judge can't carry that and what is that called? And go behind and catch him. They have to do that. Okay, so in some sense, the seat is away from there. The legislators, what do? They legislate. That means they make law. They say this will be the law in the country. That will be the law in the country. I don't follow. What will they do? They have to make sure that someone takes action against me. They cannot do it directly. Okay, the executive portion does that. Okay, so now let's focus on execution, executive part. Where are all the real seats of power in your knowledge? Which offices really hold power? Prime Minister. Okay, that is one that's real holds power. Of course, Prime Minister is supported by cabinet and all that. He can't do that, whatever. President, normally whatever the cabinet says, the Prime Minister, the President has to agree. There are only very few things where he or she can, ask for reconsideration. After Prime Minister, where is the next seat of power? It's federal system, no? There is center, there is state, Chief Minister. So after that, where is the next level? District Magistrate. So PM, CM, DM. PM, CM, DM are the centers of power. That power is not this power. That power is not this power. That power is influence, that is authority. This power doesn't mean authority. This power is the rate at which work is done. Rate at which one form of energy is converted into another form of energy. Okay, rate at which energy is consumed by something. Consumes means energy doesn't disappear. Energy becomes some other form. Rate at which energy is consumed by some, let's say, some load, resistive load. What is happening? It is converting it to heat. Okay, so this is rate of energy, rate of work done. It goes at that. But that power is different. So this is power. This is something we have studied at the high school level. What is electronics? What is electronics? It is based on semiconductors, right? But question I'll ask you is electronics, right? It comes from electron. The way I see that, electron, electronic. What is it to do with electron here? You get my point? You get my point? Is it electronic? Are you using electrons? Hey, you're doing electronics, you're studying electronics there? How many electrons are you handled? Which orbital electrons? Is my question clear to you? When he says I'm doing electronics, I may imagine my physics book and shows some, this orbital, that orbital, this and all that. Doesn't seem to be the electron that he's talking of. Subatomic particle electron. Correct? Electronics seems something else. And somebody uses the term semiconductor. How electronics and semiconductor are related? I still don't know. You understand? Okay, so now this is power electronics. If I ask a question very honestly, do we know power electronics? That we includes me also. Or do we not know power electronics? What is the answer? What is the answer? I'm asking myself. Don't be afraid, don't be shy. Worst case, they'll don't worry about what others are saying. We'll be talking more about it. Do I know power electronics? I don't know power electronics. If you cannot answer for yourself, tell. Does Professor GN know power electronics? Or he does not know power electronics? You won't be penalized for this. Don't worry about it. No consequences. You're not going to lose marks. You will not lose a job opportunity. Nobody will stare at you. Does GN know power electronics? Or he does not know power electronics? What is your answer? What is your answer? Let's get that lady in between. Get up. Do I know power electronics or don't know power electronics? What is your judgment? I don't know. I know. I know power electronics. You're saying for political correctness. That is what is politically. The answer is not. What is expected answer is what is there. What is the expected answer? If you give the answer, then they should give you marks or whatever. I should be out of that. Now, this obsessed man, we have talked to him. Now we'll talk about someone else there. Sir, at the end, do I know power electronics? I don't know power electronics. Because I didn't want to ask you. I didn't want to say, do you know power electronics or you don't know power electronics? So you may feel jittery. No doubt he's the HOD. You see why he is HOD. He says no doubt. Okay. What is your answer anyway? Let the kid give an answer. Do I know? Does GN know power electronics or he does not know power electronics? See, there's no need for workshop. There are several people sitting here who can give this workshop for you, Suresh. What are you doing? Thank you, Kanna. Thank you, Shriram. You know something, but you still don't know many things. Okay? If you are absolutely ignorant of the term called power electronics, you will be happily doing something. Some stock market, right? Something you may be doing, some bank clerical work, something you can do. Agriculture, so many things you can do. If you are absolutely ignorant of power electronics, you are not going to be coming here. Replace power electronics by electrical engineering. If you are absolutely ignorant of electrical engineering, you are not going to be here. You don't even know the name. If you know everything about electrical engineering department, EEE department is not needed. Vaijayanti madam does not have to teach a class for you. You know everything. So the trouble, the fact or the trouble, whichever way you use that, we all know something. We all know something, but we do not know everything. That, like that man said, he is last but not the least. He's sitting in the last row, but don't rate him the least. Okay. So yeah, don't be wary of all these kind of comments and all that. You have to free, you have to be open, right? That's when learning has to happen not under tension. It should happen in a relaxed atmosphere. And relaxed where it's not relaxed meaning not that relaxation. Relaxed as you are in a football field. You'll be waiting for that, yeah, right? You are always having the josh. But there is no pressure. Oh, what do we do for assignment? 9 o'clock it is due. Not that kind of a pressure. You understand? The closest I can think of that is if you are all playing, I hope that you would have played. Have people totally stopped playing now? They're still playing. They still play. I'm thankful because many people are telling me they're not playing, they're only looking at phones and all that. I saw kids in the train also. The kids are doing only this. Right? So, very good. That is the closest I will say. What should be the mentality in a classroom? Very similar to what it is in a playground. Your focus is on the football. Your focus is on the fellows next to the football. Your focus on how to take it that side. You're 2 goals behind, you're under pressure. But you don't give up. You don't give up because even the last 2 minutes you can score 2 goals. Again, game, I don't mean like game where you can stand like this for 1 hour, 2 hours. And occasionally a ball will go there. You know what I'm talking of. Right? And the ball goes, it's gone. So by game, I mean games where you are really engaged. You're focused. That is how a class must be. You have to be focused. You should be free. You should have energy. You should have enthusiasm. Right? That focus doesn't mean stress. Oh, sir, I'm under stress. I don't know how many times I would have heard this word. Okay? It's very stressful. Stressful. To me, stress is what physics teacher told me. Stress and strain. I said I only see strain because I was working 12 hours yesterday. So there's a strain on my body. What do you mean by stress? I don't know. 12 hours if you work, there is strain on your body. But what is stress? Okay, let's revisit that. This is something that I would like to say. So power electronics, so we have still not been clear about electronics. So that's the first thing that we will do when I get started off in another 3-4 minutes from now. Okay. And as you already said, power semiconductor devices are used. And we know how the devices are used in power electronics. The devices don't work as amplifiers. The devices don't work as amplifiers, right? So can you name any semiconductor device that is used in power electronics? Kriti, can you name some power device? IGBT. I'll expand it for you. Insulated gate bipolar transistor. What do you do using that? Do you make an amplifier using that? Do you make an amplifier using that? So what do you do using that? You use it as a switch. The IGBT that Kriti is talking of is either on or off. It is switching. So semiconductor devices are used as switches. See, whatever we understand, let's record, let's clarify. They are used as switches. Switches are only either on or off. On means they are conducting a lot of current with very little voltage drop. Off means no current. They are blocking huge voltage. Right? Nothing happens. Only in movies this can happen. 2 trucks will come on both sides. The hero will stand in between. The truck won't move. Come on, man. But he's hero. The director has said that. So, the only equivalent of that Bollywood hero I know is power electronic switch. 1.5 kilovolt switch will be off and handled. There is no other equivalent I can think of. Time and again we'll think of equivalents, right? Can a motorbike fly over? When you are riding a motorbike, can it fly over? It cannot. I'll tell you of instances where it can do that. Motorbike will fly. Go over a level crossing. Are you seeing that? Go over a train. It will go higher if the heroine is sitting behind. And if the heroine is in trouble, this will even go and catch a helicopter. Right? We will also see some examples where things happen, where there are conductors that do not go through certain channels. Have you heard of MOSFET? How many of you know the operation of a MOSFET? Just raise your hand. How many of you know MOSFET of an operation? MOSFET operation. Raise your hand. You have studied a course on electronic devices? Raise your hand. If you have studied a course, yeah. You have not studied a course on electronic device? Raise your hand, man. So you have studied MOSFET. Okay, put your hand down. Is there a channel called, something called channel in a MOSFET? Okay. So when higher and higher drain source voltage goes, what happens to the channel? The channel shrinks at one end. After that, what happens? There's a pinching off. After that, there is pinching off. After pinching off, what happens? There's a small reduction in the length of the channel. There is a small reduction in the length of the channel. So that L becomes L minus delta L. Have you heard this? And that is why there's a small increase in the current. So we'll probably see that later. Okay. There, the conductors are flowing not through a channel, but because of a high electric field. So I say that these conductors are like James Bond. Because we can ride only when there's a road. James Bond can ride when there is no road also. That is the closest example that I can give you compared to what happens in a movie. Right? Motorcycle flying or a train. Okay. So we will come back to the question of what is electronics. I'm having the question, how is it related to electron? You understand? That's my question I want you to answer. I'm giving you some 8 to 10 minutes from now. I'm going to come back to this question. Is it related to electron? How is it? Clear? So don't think that getting an answer to a question is what is learning. Even raising a question is learning. Even raising a question is more important than that is there is confusion. There is confusion. There is lack of clarity. What you should do when you have lack of clarity? Gentlemen, what will you do when there is lack of clarity? You. When there is lack of clarity, what do you do? Professor has taught you something, you are not able to understand. You're going back and looking at the notes, right? He has taught you on something. Give me one example what he has taught. Why are you looking at him, man? You are a student here. So what has he ever taught? Say one topic. Say one topic. What property? What is he saying? That is all right, Kanna. Tell me one topic you have learned in the college. One topic. In power electronics, give me one topic. Which converter? Okay, DC-DC. Again, which DC-DC converter? Boost. Let us say I don't understand boost converter. How can voltage increase? Right? That is confusion. I don't know. So what should I do? Sit down. I must convert the confusion into a question. I must convert the confusion into a question. What is that I don't understand a boost converter? Boost means what? Secret of my energy? Secret of my energy? Whose energy? You are all little younger. You all know only Virat Kohli, Virendra Sehwag and much younger than them. I don't know who is younger than them. After that, don't ask me. Sachin Tendulkar used to come for the boost advertisement. He used to say that, oh, boost is the secret of my energy. But that is not boost converter. That boost is different. This boost is different. But there some underlying principles are there. Okay, there it boosts your performance. Here, it is boosting the voltage. So I can understand how voltage can reduce, but I cannot understand how voltage can increase. You get my question? That is the question. I understand how voltage can be reduced with switches, but I don't understand how voltage can be increased with switching action. You get me? That is what confusion becoming question. Then you will get an answer to this. Okay, again we will do this in the afternoon. I'll ask this question. How can you boost with voltage? Clear? So this is what I do with power electronics. Clear? Now, with power electronics means you have already said there are power converters. There are so many power converters sitting there. You said DC-DC, DC-AC. What do those converters contain? Mostly switches, power semiconductor switches. Other than that, what do you have in a buck converter? You have inductors, you have capacitors. You have diodes I count them as switches. Okay, you have inductors, capacitors, right? So they are passive components. And forget capacitors, they are made and you bring to the lab. Inductors are something that you design yourself. Inductors, transformers are something you design yourself. So you need to know about inductors, transformers, capacitors, right? And if you extend that, what is called as a rotating transformer? An induction motor is called as a rotating transformer. So somewhere when the rotation starts coming, they are also related. Okay, inductors, transformers, they have windings. Machines also have windings, but there is no rotation in the transformer. But there is rotation here. So let us look at rotating machines. Let me look at rotating machines. So we are going to look at power electronics, right? Machines. We're going to look at machines. What machine? Electrical machines. Okay. And when you have this machine, it's not enough if you have the machine should do what you want to do. The machine can be in your electric vehicle, right? What should you do? You should, right? If you say throttle, will you buy that scooter? Will you call that even a motorbike? You get my point? What are you doing? Full throttle. What happens to the vehicle? You get me? Will you buy that? No. Right? So you should control the motor. You should control the motor. How will you control the motor? Using the power converter. Using the power converter, you have to control that motor. When you control that, you call that as drives. Okay? That's about half an hour. We have only seen what is the topic. Clear? This is now what we are going to get down. So we know a little bit of everything, but we have to find out something more. We have to know, see, I don't know enough of power electronics. That's why I've come here. That's why I've come here. He said, you know more. That's why we have called you. He is gone now, but he'll come back. Tell him, I do want to learn more. That's why I'm here. Otherwise, why should I put on my shoe, pant, shirt and go and teach, do research every day? If I've known, I'll be happy. Okay, I'll do something, right? Sit under a shady tree, sleep for some time, put a mat. So many things can be done. So I do want to learn from this workshop. That's why I'm here. So I'm going to ask you about power electronics and going to ask you about what is electronics. Clear? So we are going to go one by one. And now, how do I save this? This is all, if at all you want, this is my only slide now. You come, what is it? Yeah, he knows. Huh? Hey. Come. It is not saved, I think. Keep. Okay. Okay. Very good, man. High technology. Very good. Very good. See, I'm learning. PPT, how you can do things, technological advancements, adapting to that. Huh? I want to put that right down. Okay. What happened? Okay. Now, okay? Okay. So we are going to get in the technical topic. What we are doing, we've introduced that. Before that, I just want to tell a little more about learning, the first part of that. Correct? Let us define learning. Let us define learning in a very simple way. Okay? So what do you think is learning? What do you think is learning? What do you think is learning? Put it in any way. There is no correct answer. Do you know how to learn? Yes, I know, but I also don't know. Same answer as in power electronics. What do you think is learning? Start with questioning. But answering question, that is an aspect of learning. Answering question is also learning. Okay, I'll complete that. converting a confusion into a question or a set of questions. Okay, and answering question, and even finding out what does it take to answer certain question. I'll put that at 3 levels. This is something I'll quote my professor, Professor V.T. Ranganathan. I think Vaijayanti and Soumitra will know them very well. Whenever we go with the confusion to his office, I said confusion. You don't know, you're not clear about something. It's not with a question. Okay? Yeah. He used to say, sit down. Okay. Let us understand what we know and what we don't know. First statement. Or let us understand what we understand and what we don't understand. I don't know direct torque control of induction motor, but I have to break that. Do I know an induction motor? Do I know the principle of induction? Do I know how principle of induction is being used in the motor? Okay. Do I know what is torque? Do I know how torque is developed by the motor? Right? Do I know how to modify the torque? Who modifies the torque? Which quantity? How do I change the quantity? So how can I control the torque? What do you mean by directly controlling the torque? It is asking him to control the torque or directly asking the motor to control? I say, Professor Das, please do that. It is indirect control. I am directly telling the motor, please, it's direct. Is it like that? Right? What do you mean by direct? You understand? There are so many questions. When I say, sir, I don't understand direct torque control of induction motor. Question is, what do you understand? What do you don't? Let us understand what we know and what we don't know. And once that clarity comes, then I know, I don't know, I'm uncertain. White, black, gray. The gray can become questions. It can actually become questions where I'm confused about. Gray is not in between black and white. It is totally out. I'll wherever I don't those confusions, I'll make them into questions. And I'll try to answer the questions. Doesn't matter if all the questions I can answer today. I've at least listed down 5 questions. Tomorrow I will think that question 1 and 3 are actually same. That's also finding. You understand? Then one by one I'll find out answers to them. That is how you deal with that. So see what you know, what you don't know. Then I know, I don't know. I can't say whether I know or I don't know. That confused state should become questions. Then all the questions must have answers one by one. You can link all the answers together and become a proper mass. That is one way. So this is a complicated process enough. This is a complicated process enough. Anything that is complicated will not work. Anything has to be simple, at least at the starting point. So I want a simpler definition for learning. I want a simpler definition for learning. What could be a simpler definition for learning? Try that out. Break only one of it. Okay, I'll suggest something. Can you learn something without knowing anything? Can you learn something without knowing anything? What is my name? Let's say you don't know. I'm saying my name is G. Narayanan. So prior to that, you don't know my name, but you know that I'm a human. You know that I must be having a name. You understand? Without knowing those, you can't be asking me questions. Correct? Does a cat come and ask me, what's your name? The cat can't speak. That's a different issue. But assuming it, will it come and ask? No. Yes? So, let me put my idea because it could be a little abstract. I would normally like to look some boxes and all that. And I'll say, this is unknown. I think I'm back to my problem. Find their options. Eraser. Okay. Something I'm doing. Eraser. Yes. Yeah. I think my pressure is higher. Okay, clear everything. Just clean the whole thing. Hearing, that's all easier. Okay. I will write that. So with hand it will draw. With hand I'll do that. Huh? Oh, I have to do this. This I have to say. Yeah. Okay. Good. Okay. There is something unknown. I'm writing that So when I'm learning, I want to learn something that I don't know. Let us look at the ethical human part of it first. I have to acknowledge that I don't know. I have to acknowledge that I don't know. I feel like, I'm an all-knowing Brihaspati. I'm never going to learn. Big mistake that probably many of us do. I'm not qualified to criticize. Nevertheless, I realize or recognize we sometimes put a cloak of pretension that we know everything. We feel insecure to say that I don't know something. We don't want to say, and many times that is insecure. If I say I don't know this, what will this young man think? What will that girl think? He's a power electronics professor, he's doing this. You understand? All that will be complications. Many of them may be my own imagination. And even if it is true, there is nothing I have to worry about. I have to acknowledge the fact that I do not know that. I have to acknowledge the fact that I do not know that. Next, I have to say, I want to know that. There are hundreds of things, millions of things that I don't know. How many stars are there? We don't even know them. I want to find out some star that is in the neighborhood of some other star. I don't know. Those are all I will never know. But some things I want to know. I don't know and I want to know. This is something, there's another professor called Ram Narayan. He used to say this directly and indirectly. Unless you acknowledge that you don't know something and you invest to know that, you should have motivation to know that. You should have, I want to know. When I say I want to know, you hear the stress in that want. That means I have motivation to learn. I want to know. That's not what I'm saying. Get me? There should be motivation. That is why I'm saying strength is necessary. That is why, why sandwich you have to eat in the morning? You need that. Okay. I want to know. These are necessary conditions. These are necessary conditions. Okay. So then, by God's grace, it's not that I know nothing. I know nothing. I was writing this, no? This is better. Some things I know. Some things I know. Many times, that known precedes unknown, you can see them very clearly. Okay? You would have done some course in your first semester, some other course in your second or third semester. You understand? Can you give me some links like that? What all courses you have done? Have you done some mathematics? When did you do mathematics? First year. Did you do some calculus? When did you do calculus? First and second semester you did. What calculus? Did vector calculus. Right? Did you do vector calculus? What is vector calculus? Okay, grad, divergence, curl. Did you do all that? But did you do just calculus prior to that? Differentiation, integration? Yes? So you could not have gone to vector calculus without knowing calculus. Correct? F of x is equal to sin x. What is f dash of x? You would have done that sometime. Correct? Class 11 or so. You would have read and that. So you would have done differentiation. You would have done integration. And these are necessary for you to solve differential equations. Correct? You understand what I'm saying? Solving differential equations is necessary for you to solve partial differential equations. In vector calculus, you will have a lot of partial differential equations. The vector will vary with x, will vary with y, will vary with z. You will do dou v by dou x, dou v by dou y, right? All that you will be doing. You understand? So you would have done calculus and you would have learned vectors. You will know vector has multiple dimensions, right? And with that only you will go to vector calculus. You understand my point? So some things if you have to learn, some things have to be known. Some things have to be known. In the academic parlance, they call it prerequisite. When you go to a course, they'll say prerequisite. You want to learn power electronics? So what's your name? Shashwat. Shashwat wants to learn power electronics. So he'll be given prerequisites. So power electronics, welcome. But you should know 1, circuit theory. 2, electronic devices. 3, control systems. We'll give some list. Then you come to the course. You understand? So this is called prerequisite. So sometimes late. But many times we imagine that we go from known to unknown. This is learning. This is learning. This is learning. But many times we imagine that we have to move only from here to there. But there are so many other things. There are so many other things. So like what? Other topics. Other topics, same subject. Sorry. Same subject. Okay. This can help me. This can help me. Okay. It may look a little abstract now, but we'll make it a little concrete. And not just that same subject, can also be other subjects. Can also be other subjects. This arrow mark is my learning. This arrow mark is my learning. And learning, you can take many other support. Not just the direct prerequisites. It can come from many other sources. Okay, which are related to that. So one way I will say, for example, known to unknown. Like we already discussed enough examples, right? Calculus, differential and integral calculus to differential equations. Those are all one after the other. And calculus to vector calculus, right? Similarly, there can be multiple things here. I know DC motor. I know chopper. I want to know DC drive. Right? These are like, so sometimes there are related topics. These related topics, for example, can come from something, right? Very close to that. Something can be somewhat distant subjects, like it can be from control, electromagnetism, field, circuits. Sometimes it can even be far away subjects, like English, like language. You remember in our conversation, at least 10 minutes or so we might have spent on language issues. Did we speak about that? Noun, adjective. Did we speak something of that? Words having same meaning. Why did we do all that? Was it wasting time? Was it wasting time? Language can also help you learn. Language can also help you learn. So this is what we are going to do. In a nutshell, what I'm going to say is we are going to leverage many topics that we know. We are going to leverage many topics that we know to learn what we want to learn. Clear? That's my next point that I'm trying to. This is a proposition that I'm giving. So we will now take up some exercise. Okay. We don't know something and we want to find that out. How we can leverage. Okay. I'll tell you one of the first things that we will do is we'll try to understand what is electronics. First question is we'll try to understand electronics. Next is, because again it says electronics, do you know? Yes. You don't know? Yes. Both are correct. I know something, but I don't know what it is. Clear? So what is my first question? What is electronics? Second question, take more specific example from electronics. What is the simplest electronic device? Diode. What is a diode? What is a diode? These are the two questions which we are going to go from the unknown to known. What is known? We know something about it. We will marshal all that. We will marshal everything else from the top and bottom, and we'll try to better understand electronics and better understand diode. So okay, that's what we will do in the next few minutes. When is the next break coming? 11:15. Okay. 11:30. Okay. So at this point, I want to say something. It's a little. How many of you can understand Tamil here? 1, 2, 3. Very good. How many of you can read also? Okay, at least 3 of you. Okay. So I'm going to write something. Is my handwriting clear? Read it out. Katradhu, She knows what I'm. Don't worry, for others, we will soon do what is this. Our madam will tell us what does it mean. Katrathu kaiman alavu. Okay. Then kalladadu. Man. Huh? I know. But still he knows. There are many people who may not know this, no? Katrathu kaiman alavu, kalladadu ulagalavu. Okay, alavu comes in both the cases, right? That means a measure. Okay, this who is missing here? My writing. Okay. Alavu means a measure. Katrathu means what I have learnt. Katrathu means what I have learnt. This is ancient wisdom. Somebody said this maybe 2000 years back or whatever. Long back, when most people in this planet did not even know that they should wear a dress. Okay, that old. That somebody said this. Katrathu means what I have learnt. Okay, kalladadu means what I have not learnt, what I am yet to learn, what I don't know. So you understand that. Katrathu is the first box. Kalladadu, the potential candidates is huge. The potential candidates is huge. Kalladadu. Now, kalladadu ulagalavu. Ulagam means whole globe, world. What I'm yet to learn is the size of this world. Okay, if I compare it to the size of the world, what I have learned is kaiman alavu. Kai means hand. Man means mud. You take some mud in your hand, you hold. That is all what you have learned. Is the meaning clear? What I have learned is what is only a fistful of mud in my hand is equivalent to the size of fistful of mud. But what I'm yet to learn is the size of the whole earth. Okay, this is ancient wisdom in this country. You will find equivalent statements in many languages. I'm saying this from my mother tongue because that's what I know. You will find equivalent statements, many things like this. Okay, so there is nothing wrong in not knowing something, but there is everything wrong possibly in not making an attempt to learn when it is your job to learn. When it is your job to learn, if you have not learned something in political science, it's fine. But if you're not making an effort to learn your electrical engineering, you are having a trouble. Okay, it is dereliction of duty. You're not doing your duty. So this is something, first part of it. Next one, I will not write that. It will take longer to write. I'll again say something in Tamil. I'll translate that. Okay. So, ஒருவன் அறிவானும் எல்லாம் யாதொன்றும் அறியாதவனும் ஒருவன் குணநடங்க குற்றமில்லானும் ஒருவன் கணநடங்க கற்றானும் இல். Is anybody able to follow it partly? At least the words? You are able to follow. You are able to follow. You are able to follow what I said. I'm repeating that. ஒருவன் அறிவானும். I'm not singing that. I'm not playing the meter. அறிவானும் எல்லாம் யாதொன்றும் அறியாதவனும் ஒருவன் குணநடங்க குற்றமில்லானும் ஒருவன் கணநடங்க கற்றானும் இல். Okay, so ill means no, illai is not there. Who is not there? ஒருவன் அறிவானும் எல்லாம். That means one who knows everything. ஒருவன் அறிவானும் எல்லாம் இல். There is no one who knows everything. So that's almost same like what you have here. The next line is where we have some sucker. யாதொன்றும் அறியாதவனும் இல். யாதொன்று means nothing. Okay, அறியாதவன் means knows nothing. There is nobody who knows nothing. There is no one who knows everything. There is no one who knows nothing. You understand that? You can never say, oh, no, I don't know. Pata nahi chal raha hai yaar. Don't cry. Don't cry. In fact, that weakness is something that I am unable to tolerate. If I have a bad name with the students, that's that. When somebody says, no, I'm not, the weakness, I feel like thrashing. I don't show sympathy. If a person is injured and he cannot walk, well, I'll help him. And you say that, no, I think that's the correct treatment. Politically incorrect, but do the equivalent of this, the legal equivalent of this, of thrashing. You can't walk, man. Look at the 80-year-old man going. Feel like, this is Narayanan. This is Narayanan. I may have to temper this a little bit here, there. Whatever I said, don't do the literally, but you have to do the legal equivalent of this. If your professors don't do this, they do this, don't mistake. You understand? This is something to be done. I never sympathize weakness. Not real weakness. You would have got weak because of dehydration. I sympathize with you. That weakness is because of your mental thing. You're thinking, you're not, lack of confidence. Lack of confidence, I feel, has to be thrashed. Exorcised. EXOR. Okay. EXER. See, exercise is the way to exorcise that. Okay. Thrash yourself. Don't never feel weak. Okay. People have found this out. It's all that you're not doing something that is, only the sages can know. Many people like us have learned all this what you're doing. So you can also learn that. So don't ever feel miserable, bad. I'm weak. I'm very weak in this subject. What the hell are you talking? Is my real response. If you want to learn, yes. But that's why I said I know. I don't know, and I want to know. If I'm truthful to I want to know, I will certainly find the resources to do so. So coming back to the second one, the first part says, no one knows everything. Oruvan arivanum ellam ill. Yadondrum ariyadavanum ill. The ill is common. So there is no one who knows nothing. Again, the third says, Gunanadanga kutramillanum oruvan ill. That means one who's called nirdoshi, who has got all the positive qualities, who doesn't have what is called as dosh. Such a person is not there. Such a person is not there. You will find fault with anyone. The best of the man, you will find fault. Even God comes also, you will find a fault. Okay, so no such person there. So you should not go picking, oh, you did that, you did that. Everybody can do mistakes. You look at your mistake and correct yourself. That's better. Then, Gananadanga Katranu Mil means who has learnt everything, who has learnt all the books or whatever. So the first two are really operative. There is no one who knows everything. There is no one who knows. So with this, the kind of philosophical aspect of this is over. Now we are going to get into the technical aspect of understanding what is electronics, what is diode. Those are the only two things that we will do prior to this. Now I just have to move to the next one. How do I do that? Just next slide. Very good. Okay, my confusion about electronics. Correct? I don't know what is electronics. So let me write down. What is electronics? Okay, that's my confusion. That is my confusion. I don't know what is electronics. Correct? Now, I think I started here. This is noun. This is adjective. Okay. Here also I don't understand. Here also I don't understand. Okay, I'll tell you why I don't understand. This is one usage. Electronic spin. Electronic orbital, right? Whatever path. These are all the kinds of terms my physics teacher used. These are all the kind of terms my physics teacher used. If I listen to what defense minister is saying, defense minister says, which shell, sir? Which subshell, sir? Is my question correct? Yes or no? The finance minister says, electronic commerce. He says, he or she says commerce, electronic commerce. They say, which electron is going? Is my question correct? I'm having a point here. Okay. So I have a confusion about what is electronics. Is it coming from electron or is it something else? That's one confusion. The usage of electronic. Is my question clear to you? Okay. How do we solve this? I can also say something more. Okay. Friend says email. My friend sends me an email. My friend sends me an email. Which variety is that? It is of the electronic warfare variety. It is of this variety. So the same electronic, I'm able to club them into two buckets related to electron, related to a subject called electronics. The first electronic spin and electronic orbital are related to electron. Electronic warfare, electronic commerce, electronic mail are related to the subject called electronics. The subject called, and both are nouns. Electron is also noun, electronics also noun. Not language, man, noun, adjective, noun. Big confusion. Okay, so how do I solve? Can you solve this question for me? Or you want me to add something more? Better you add something more, no? Why should I? I will conserve my energy. What, Shashwat? Good. So, there are many terms like electronics. The confusion comes from language, right? Okay. If you ask Dr. Manmohan Singh, he will say, they are very similar. The words are very similar. Where does this originate from? There's a word called electron. There's a word called, okay, I think by the time I learn this, you are going to run out of patience. Okay. Yeah. Better read that as economy. That is economy. Economy is a noun. Economic is an adjective. And from there comes economics. Related words. What does economy mean? Whatever it is, or wealth, production of wealth, right? India is the what, fifth largest economy, fourth largest. It will become the third largest economy very soon. So you understand what is economy. What is economics? Study of economy. This is my confusion. Economics means study of economy. Does electronics mean study of electron? This is my confusion that has been working on me for all this time. That is what only now I am successful in putting it across to you. You get me? Economics is study of economy. Electronics must be study of electron. I can write electron, electronic, electronics. Electronic and electronics. Very similar. So why is the confusion? The points are clear to you? So, central question, ये electronics, ये चीज electronics, ये क्या होता है यार? That confused, that because I can't ask now. Why? I have joined National Institute of Technology. Now I cannot ask you electronics. Which department? I'm in electrical and electronics engineering department. Now I can't go and ask someone, sir, what is electronics? Madam, what is electronics? Correct. So that is why I said, you should know that you don't know. You should admit and you should want to know. These are necessary conditions. If I don't know, I'll ask Soumitra Das. What will he think? That this professor doesn't know. Let him think. That is not my concern. My concern is that I should learn. What he thinks or what someone will think is not my. But if you think, it's something, is my stomach going to get filled? I'm hungry. I have to eat. Right? I can't think that this gentleman will think he's eating more roti, that man will think, I can't do that. I have to eat. So this is again my hunger. Okay. So I want to understand electronics. That's my question. So what do you mean by electronics? Why this confusion comes with electronics? Is it study of electron or is it something different? Answer the question. Is it clear now to you? Is it clear to you? Economics, I've clearly told you. Economy, clear. It's a noun. Economic means what? Economic sanctions have been imposed on Iran. We are making economic progress. Adjective. And you add an S to that, and that becomes a noun in English. That means study of economy. Right? So electron is that subatomic particle. Electronic is something related to an electron. And electronics must be study of electrons. If they teach you about electrons in electronics, you didn't ask them. You must have asked your sir and madam, tell us about this electron, tell about that electron. You didn't. Why? Because it is not study of electron. Because it is not study of electron. Then what is it? Study of? He's bringing something on study of flow of electrons. Why should electrons flow? Study of flow of electrons. He's trying to give a twist to that. There, we will not take it as electron. We'll say flow of electron. Why is it like that? There's a potential difference, but that's an unknown word now for me still. Something is pushing. Pushing what? An electron. So what can push an electron or what can pull an electron? An electric field. An electric field. So what is happening in electronics? Electric field is there. No. Did you study about electric field in electronics? You have all completed electronics course. Did you study? Yes? Yes? Yes or no? You studied before that, not in the subject. Did you use the knowledge of electric field in electronics? You have used. I will come to that. So then, but still I'm not getting an answer. Study of flow of electrons. Flow of electrons, madam told me, is current. So study of current. So it must have called currentics or something like that. Currency. That's different. Currency also flows. Okay, that is why it says something. Okay, there is no currency means it doesn't flow. Okay, what is current? Current means what is present now. So many meanings are there for that. So language is very, very important. Many times I say, when you come up with a term, right? Many times we assume that we know terms. In a class, if you sit at the end of the class, 15, 20 terms, you will be able to count and say where you have assumed the meaning. You have not asked yourself what is the meaning of that. Okay. Let us make a thyristor chopper. Professor will say, let us draw a thyristor chopper. Draw is probably the only term that I know or I don't want to question. Drawing also is there, like drawing water from well is also there. Correct? This is not the draw. This is drawing. Thyristor, am I sure? Something with that symbol. Chopper. Right? Chops. You have cucumber. Chop. I have salad for summer. That's not what we are doing. Why is it called chopper? I don't know. You understand my questions? There are so many things that we don't understand. We don't bother to ask ourselves. We do not bother to ask ourselves. And when the situation emerges where the question is raised, that may be in an exam or that may be in practical life, you are stumbled. You are stumbled. I sit in madam's class. I listen to her. At least 20 terms, I don't understand what exactly they are. Roughly, we imagine, that is what it is. And we are going based on that. There is no clarity. Do you agree with me? Do you agree with me? If we correct this, our effectiveness will be very high. If we correct this, our effectiveness will be very high. Voltage. Do you know what is voltage? I can't ask. No. Come to electrical department. Don't ask what is voltage. Not different from old age. That I understand. Old age and voltage are different. That much is enough. So we are not understanding. So there has to be, if 80 of us are sitting here, when any of us use a term, all of us should understand it by the term. Correct? Desk. All of us know what is a desk. Monitor. All of us know what's a monitor. Board. All of us know what's a board. Fan. Roof. I'm not saying roof and you're not seeing this. All of us are on the same page. This is not happening with our technical terms. This is not happening with our technical terms. I'm raising so many questions on electronics. Are these questions valid or not valid? Are these questions valid or not valid? So why is it that you did not raise this question? I'm curious to know. I'm curious to know. I'm not being accusative. I'm curious. Why? Why should you fear? Why should you? Whom are you fearing? Whom are you fearing? You have some self-image in your mind. You are fearing that that image will be destroyed. Nobody created that. You have created that. I am thinking that, I'm next to Maxwell. I'm nobody. I'm just Narayanan. If I create a false image, who is responsible for that? Nothing ever comes out in science unless you really go down into that. Okay? So that fear is not of someone else. It is because you are worried about certain image that you have created yourself will be destroyed. Go it on. Ask this. Make that as a habit. Every term. Sometimes the instructors might feel a little discomfort. What are you asking? Better feel discomfort rather than suffer ignorance over a longer period of time. I remember in 11th standard, we challenged our professor, our teacher at that time. I think there's a madam called Jasmine. She had just finished her MSc MK. We gave her such a tough time. Okay. She wrote dy by dx plus y is equal to something. She was trying to solve that. Then she said d by dx plus 1 the whole into y. You understand what I'm saying? dy by dx plus y was the left-hand side of the differential equation. She wrote that as d by dx plus 1 the whole into y. All hell broke out. All hell broke out. Madam, sine x plus x is sine plus 1 the whole into x. That was yours sincerely. 5, 6 people on their feet, giving all kinds of example. You can't do this. You can't do that. She was struggling. I still remember that. I still remember that. It is not that you can do it like that. Somebody realized that the differential equation has an equivalent algebraic equation. And if you solve that algebraic equation, the roots to that algebraic equation will take you a long way in solving the original differential equation. You understand? It is not d square y by d square by dx square plus d by dx plus 1 the whole into y. That's not correct mathematically. In structure, it is similar to certain polynomial. That polynomial, you can find out the roots of the polynomial. If you can find out the roots of the polynomial, these roots will tell you something about the solution of the differential equation you are concerned about. Get me? So it is not d by dx plus 1 into y. You are only trying to make that into an equivalent polynomial. If you really read the arguments, math is a very, very rigorous subject. Unless they had explained, no mathematician will ever accept. Fourier was in trouble. Did you know that? Fourier was in great trouble. So what do you know Fourier for? Fourier transform. Before that, Fourier series. So what does he say in Fourier series? Any arbitrary periodic signal can be converted into a set of sine waves. A set of sine wave. So they asked him, any periodic, is it correct? He said yes. So the periodic signal can be continuous. The periodic signal can also be discontinuous. They asked him, is it correct? Fourier said yes. Fourier said this applies to discontinuous functions, periodic which are discontinuous, like square wave. Right? Discontinuous. You are applying Fourier series. Right? You are saying, 4v by pi, you are writing all that, fundamental component. They are saying, what are you adding? Sine. Is sine continuous or discontinuous? Continuous. If sine is continuous, sine x is continuous, sine 2x, cos 2x, cos 5x, all the harmonics are continuous. How can you add all continuous functions on the right hand side and get a discontinuous function on the left hand side? Is the question clear? You add whatever you add, no problem, man. You add whatever you want. You add 80th harmonic also. All the 80 harmonics are continuous. My sum has to be continuous. How can you say that that is a discontinuous function? Have you heard about this? Have you thought about this? The moment somebody writes sine waves, this should occur to you. Why are we using sine waves? We've slightly deviated. I will come to this question in my fourth session. On while we deal with machine, right? Many machines are sinusoidal. So I'll ask you this question: why are the generators producing sine wave? Why are the generators producing sine wave? Okay, be prepared for that. Now you are getting all this, adding that. So what is the solution? What was the kind of answer given to this? Fourier series approximates. Okay, at the point of discontinuity, the summation is not a representation of the signal. It is the average of the left hand limit and the right hand limit of the discontinuity. You get my point? Left hand side is a discontinuous square wave. It is minus V plus V. Average of minus V and plus V. Minus V is the left hand limit. Plus V is the right hand limit. Average of the two is 0. So when I express square wave as a sum of sinusoids, as told by Professor Fourier, I will be approximating the square wave. It's correct everywhere else. But at the point of discontinuity, it will be replaced by the average of the left hand and the right hand equal limits. Subject to this, you can take it. You understand? This is where the question remains. Okay, that sign is very smooth. Again, that's the point I'm telling you. That's also an answer to this now. Okay, why did I come to this question? Why did I come to this question? Huh? Math is rigorous. You can't say, oh, let's consider like that. Math is very rigorous. But mathematicians accepted something. So this is where Fourier had. And why did I go back to that? Where did I start from? From electron, how did I go into math? Huh? Y is dy by dx plus y. How can it be written as d by dx plus 1 the whole into y? If you expect a student to learn math, the student has to be rigorous. The mathematicians use a term called hand waving. They say, oh. So mathematicians don't like that. Looks okay, no. If idli is not boiled properly, what is there? Scoop out that portion, eat the remaining. Not like that. Okay. So now what is electronics is my burning question still there. My question still there. Which way I go, this way or that way? Is it electronics? I don't know where to start from, where to end. How do I solve my confusion? How do I solve my confusion? Is my confusion correct? You are saying flow of electron, he is trying to give me some answer. You should not nick these atoms. Then you won't try. You must try. You make what is called hypothesis. It's hypo, H-Y-P-O, thesis. Thesis is a position. Hypo is some kind of preliminary position. Then you will say whether it is right or wrong. You yourself will disprove that. Doesn't matter. Then it is gone. You will go to the next hypothesis. If you are able to prove that, then finally it becomes a proper theorem or whatever. You get my point? So there is no harm in coming up with that. But I'm still trying to see how to break the problem. I'm still trying to see how to break the... my confusion is correct. I'm going by economy, economics, study of economy. I can give you many examples. Ergonomics. Right? Yes, ergonomy. They say how something must be packaged, how your seat must be there. Car must be ergonomically designed. If you travel 10 kilometers, you should not get a backache. Steering should not give you shoulder pain. Correct? These are, if I hold something, It should not be difficult. These are ergonomic design. Keyboard, your pain will start. So many examples I can give. Why is it failing? So what is electronics is still my question. Okay. Now you can't give me an answer. Tell me how probably I can solve. My question stays. I've come here to raise such questions and get answers. Before I share a partial answer that I might aware of, you all may have no complete answer. My own answer is going to not be final word. Please understand that. Understanding keeps evolving, can be better and better. Okay. Now, how do I break that? What kind of, that's a jam, right? What kind of log it is called? What is that log called when we are not able to move? Huh? Log jam. How do we move? How many of you understand my question? Raise your hands. About electronics. Nobody understands my question? What is my question? Madam, what is my question? You, the second from last. What is my question? Huh? What does electronics mean? More specifically, what is my question? Correct. Roughly, more specifically. Is it study of electron or is it something else? Is my question clear to you all? Okay. Please raise your hands if you have understood my question. Raise your hands. You have not understood my question? No? You tell what my question is. You get up and tell what my question is. What is electronics? Is it study of electron? That's my question. Yes? Is now the question clear to everyone? Okay. First, then your opinion on the question. Do you think this is a valid question, worthwhile question, or it's just an absurd question? Your opinion on that. Is this a valid question? Is this a reasonably worthwhile question? Right? Okay. So now I'm not able to answer that. Okay. How do I break the jam? How do I somehow wriggle my way out? I'm caught up somewhere. Okay. I'm going to give my mind and suggest to you some, not the answer, suggest a way out. Now I have to see what I know about electronics. I have to see what I know about electronics and start evaluating it. I'm stuck with the term. Okay, there's a subject called electronics, right? You understand. So what is, can you name things related to electronics? Go ahead. Huh? Huh? PCB, transistor, huh? Band gap, huh? Atom, the subject called electronics. Okay, he is adding to my confusion. Good. Huh? Zeros and digital electronics, polarity, microcontroller. So many terms that are related to electronics. All of them, they said, are related to electronics. Okay, so I should ask some question. The simpler, the better. Okay, what is the simplest element where electronics starts off? Huh? Simplest element that you know in the subject called electronics. Diode. Correct. So my answer, I will see if I can look into a diode. Electronics means a big vast subject, like NIT Goa. I'm catching hold of this gentleman. I want to understand something about NIT Goa. Okay, where is it located? There's some information. So what do? I'm very confused. Which way is there? Catch hold of one person, this gentleman, correct? And why I catch, he is easiest to catch. Same way, I'm looking at what is simplest to answer. Where did all the trouble of electronics started? Where? That's a question that I always ask myself. When did I hear this first? Whom I heard this from? Which subject? Which teacher? In this connection, I'll ask you a question. Which is the first order system that you know? First order system. Huh? Huh? RC circuit. Huh? Who told you about that? Huh? Your basic electrical engineering teacher, somebody. Circuit theory. Huh? RCRL. Nothing before that? Nothing before that? Huh? Huh? Physics. Huh? Who said in physics? Madam knows. Madam remembers. Huh? Who told you in physics? Huh? Spring mass is more complex than that. It is a second order system. See, before first order, you have a second order system. You can't be knowing a second order system without knowing the first order. What is the second order system you studied in school? Huh? No, give me an example of a second order system you studied in school. Pendulum. All of you know pendulum. You studied pendulum in school. What is the order of the system? If you studied a second order system, it is impossible that you would not have studied a first order system. Correct? Is there no first order system that has ever told to you? Somewhere there. More complex. You don't deal with that. Huh? Come again? Huh? Newton's second law. It is not, okay, it's not first order. Okay, we'll come to that. System, some example of a first order system. Electricity and magnetism itself came much later. Physics, they would have taught you about matter, solid, liquid, gas, right? And then they would have gone to some little thing. Some electricity, magnetism, they'll touch, they'll say magnets are there, bar magnets are there, something, right? Physics, if you remember that, there will be first subject called, kinematics, something like related to motion and all that, right? Then dynamics will come, where that is about force and all that, right? These are some level, right? Next, what is the subject? What topic after that? Optics comes a little later. Simpler version of thermodynamics. Heat. Law of cooling. Law of cooling. What does it say? Rate of cooling d theta by dt is proportional to the excess of the temperature over ambient. D theta by dt is proportional to theta. Okay? And the proportionality constant is negative. That's the first order system. Okay, so we have ignored them. In my mind, clearly, law of cooling is the first time I encountered the first order dynamics. Pendulum is where I encountered the second order dynamics. It is more undamped. Okay, it's like an LC circuit, continuously oscillating, ideal LC. Of course, pendulum is not, we'll push that every time. But kids being kids, we don't recognize that. Okay, so I will look at the simplest one, that is a diode. This is the simplest material. I will try to examine whether my confusion can get solved with a diode. Okay, right? And what does diode mean? Again, English. Again, English. What does di mean? What does diode mean? 2. What does this mean? ODE stands for what? Stands for what? Electrode. What is it, madam? We are firing on all cylinders now. Unfortunately, that's not ordinary differential equation. This comes from 2 electrodes. This comes from 2 electrodes. Yeah, what was the joke? Share that. It's not that. A die, it is not capital ODE, not an acronym. This comes from electrode, 2 electrodes. Okay. This is something to do with electron. This is something to do with electric field. Okay. Now let us come and fill the gap. After the break, we will come. So after clearing this up, we'll get diode and we'll be looking at the devices and the way that you would look at it in a college now. Yeah. So we have this question of electronics. What is electronics? Whether it is study of electron, right? So to resolve that, I'm going to get into a device, and that is called diode. That is a diode. This is the simplest electronic device. This is the simplest electronic device. And here, do I get any clues to understand that? This means two, this means electrode. And what does electrode itself means? It's an electrical terminal. It's an electrical terminal. What are these two electrodes? One will be called a cathode and one will be called a anode. Okay, so I'm now looking at this device, right? So there are two terminals, one is cathode and one is anode. This is my cathode. What does this cathode do? It emits electrons. The cathode is at a negative potential. It is at a negative potential. It is heated up. It is heated up. When you heat it up, it is called thermionic emission. Thermionic. Therm means heat, right? Ion means charges. So thermionic emission, when I heat, it is ready to give out charges. It is ready to give out charges. So what is it I'm doing? Is electronics related to study of electron or something related to electron? That's my bothering me. So I'm trying to resolve that using an example called diode. I'm taking a simplest electronic entity. It can be a big system, it can be a circuit, it can be a single device. I'm choosing a device. It can be a complicated device, but I'm choosing a simple device, and that's called diode. And that's now I'm doing this positive. This fellow is capable of emitting electrons, but who will accept the electrons? Who will accept the electrons? Only when there is an anode. This is positive. This is a positive terminal. Okay. And there are so many interfering people all around. There are so many interfering people all around. If I apply this high electric field in air, what will happen? If I apply this in air, what will happen? They will be charged. They will get ionized. If I apply a potential here, air will get ionized. So I cannot be stupid to be doing this in regular air. So what should I be doing? I should create vacuum. I should create vacuum. So all these fellows are actually sitting inside a vacuum chamber. This is where electronics evolved. This is where electronics evolved. So this is going to emit and this is going to accept. Okay. So I know that at least historically electronics had something to do with electron. The name is historic. Okay. But let me better understand that. If this, what else can I do? Is it called diode? No, it is not only that. This fellow is getting heated up, and therefore he is able to emit electrons, and this fellow has positive potential, is attract. There is an electric field, right? There's an electric field. There's a force acting on a charge Q, right? What is the force acting on a charge Q? Q times E. Q times E. If you apply an electric field on a charge Q, the force experienced, and actually this is a vector, whereas Q is a scalar. Along the direction of the E vector, you have that force, and the E vector is now on this direction. Low potential, higher potential. All the equipotential surfaces are normal to this line roughly. And this is the direction of the electric field. And there is a force in the direction of the electric field. Okay. Can I make this electron move like this? Yes. What should I do? I should apply certain force on that. I should apply certain force on the electron, which will make it move in that direction. Who can make it move in that direction? Magnetic field. How can a magnetic field make it move? It is a moving electron, but how can you exert a force on a moving electron? There is another component of this Lorentz force where it is the vacuum tube diode may not be relevant, but the Lorentz force is still relevant for you. It will continue to be relevant because this is almost the only way force is experienced. So it is moving. If this fellow is moving in this direction, right? Q times E vector. What is V cross B? This fellow is moving in this direction. If I apply a field downward, then I have to rotate it in this direction. Then this fellow will come towards B. So V cross B, cross product. From V to B, if I rotate it, the screw, right hand screw will move in some particular direction. Correct? If it is like this and B is vertically downward, this is V, this is B, I will rotate it that way. This fellow will come like this. If B is upward, V cross B, I will rotate it, it will go in the other direction. Now for this to do that, I may have to apply my B horizontally from here or there. You understand? So by applying magnetic field, you can do that. And you are doing this. Have you called cathode ray tubes? Until very recently, you would have seen in childhood. Have you been watching TV? That TVs were very big in childhood. Now they have become small. Why they have become small? Because LCDs came. Earlier, the display was big. There was cathode ray tubes sitting inside. And the oscilloscopes in the labs were also cathode ray tubes. They had very long ones. So they were being used in that. Okay, cathode ray tube was one of the recent ones. Nowadays, because this is in vacuum, we call this actually vacuum electronics. We call this vacuum electronics. So you can have some grid also. There is some control terminal. There is a control terminal. With the control terminal, you can make it a three-dimensional device. It's an amplifier. These amplifiers are being used even today in radars, for example. Where the power of amplification required is very high. For someone who is asking why need that, even today, okay, there is a DRDO lab called Microwave Tube Research and Development Center. Okay, even a few years back, they were having very big research questions on how do you make these. Bharat Electronics Limited in Bangalore makes this. They are used in practical radar systems. Okay, maybe they'll eventually get replaced by semiconductor, but this is still there. So now we call all of them vacuum electronics. So it's not only two-terminal device. You can control them. You can control by putting grid and all that, and you can actually have a transistor. Okay. So all this later we started calling them as. Now let me stick to the diode. What does the diode do? Electrons flow in this direction. The current flows in the opposite direction. Current cannot flow in the other direction. Cannot flow in the other direction. That is what we started calling as valve. Okay, what do you mean by valve? This professor is troublesome. He keeps asking so many questions on language. No, what is valve? Anything that regulates a flow is a valve. Something that regulates a flow is valve. A very special condition of that is it allows flow in only one direction. Heart has valve. What is heart's job? It has to pump blood. What is the most critical organ in the body other than heart? Brain. No matter what, heart has to make sure that enough blood reaches the brain. How does it do that? Pumps up. But that is against gravity. This heart is so small. What is the size of the small? Size of one's fist. This small heart of Narayanan has to fight against Mother Earth, who is so big. What is the radius of Earth? 32,000 kilometers. How much is this size? How big is that? Get my point? Heart is pumping it against gravity. So, heart is helped by valves. What happens? When it is pushing up, what happens in the heart? How many of you have studied basic biology at 10th, 11th about heart? So, what are those valves called? There are some valves, right? AORTA. Aorta, aorta, they pronounce aortic valves. So there are valves, ventricles, there are chambers. left ventricle, right ventricle, the chambers, and what blood flows up, and the blood is not coming down. When it flows up, it will open out. Then it will stop. It will continue to do that. So that's valve. It's a very special case where it allows a flow in only one direction, and this is to allow flow in vertically upward direction. Okay. This I will say in a different context of valve. When our water supply engineers, they have a pump. They have a pump. Okay. What does the pump have? Internally, the pump has a piston inside. And the pump, let's say, pushes water. And the pump's job is to push the water up into a tank. The pump's job is to push the water up into the tank. What will happen when the pump pushes, piston pushes, go, comes back, water will come down. So there are many kinds of pumps. The one that I'm saying is a positive displacement pump. Okay. There can be negative displacement and other things too. So how do you do that? You put valves here. You put valves there. So when it pumps, some column of water will go above the first valve, some will go above the second valve. They will not come down. They will not. The next push, some quantum will get delivered to the tank. Some quantum will cross the first valve. Some quantum will cross the second valve. Some quantum will get delivered into the tank. Is it clear? Is my comparison of valve reasonable? The two different applications? The lady there. Is it clear? Valve in human and valve as designed by civil engineers. Is there a relation between the two? Correct? This is much less complicated, but it does the job. Okay, this is valve. So it allows flow in only one direction. Now, what the diode does, the diode is also a valve, which allows flow in only one direction. The diode is also a valve, which allows flow only in one direction. Okay, then what we did was, we recognized, array, don't have to do all that. Put one small fellow like this. Call it P, call it N. This is your anode. This is your anode. This is your cathode. We came to realize that there is something called semiconductor. What is a semiconductor? Troublesome, right? Kirti. Troublesome. What is a semiconductor? Neither a conductor nor an insulator. What did the physics teacher tell you? Conductor is something that conducts. Electrical conductor allows current to flow through. Insulator means no current. But remember, current actually flows through insulators. That is what is your electron EMI problem and all that happens there. In power converter, that is very, very common. Okay. So take that all with a pinch of salt. Insulator is not insulator. Insulator is actually dielectric. Okay. And dV by dt. C dV by dt is current through a capacitor. When voltage across a dielectric changes with time, current will flow through the dielectric. And what you imagine is an insulator will become a conductor. Whenever the voltage changes alone. So current will flow through unexpected paths. Insulator you will think is insulator. Current should not flow, but current flows through insulators. In power electronic converters, so you can ask a question, oh, it's a very old thing. No, today. You get me? That's where you're getting to. So you will have to have, it's only the fundamentals that will take you from everywhere. So that is an insulator. But the insulator's technical name is dielectric. Means two. There will be two layers of charges. Okay. And conductor. And what is a semiconductor? Something in between. They discovered some elements which are not exactly like them, but a little different. What is that little difference between conductor and semiconductor? Huh? Certain condition. That conductor will have a lot of free electrons. Semiconductor will have valence fellow sitting there. And some of them will come out. If you heat up, the conductor's conductivity will go down because the electrons will be agitated. If you heat up, the semiconductor's conductivity will increase because many of the electrons sitting inside will come out. Right? This is something the teacher would have told you. And the semiconductor again, this is what is intrinsic semiconductor. You can add some dopants. You can create an artificial excess of holes and artificial excess of electrons. Type semiconductor and N-type semiconductor. If you bring a PN junction like that, that PN junction becomes a valve. Okay. This small fellow is a functional equivalent of this large fellow. is a functional equivalent of the large fellow. And like not diode, you have transistor. If you put PNP, NPN, it becomes a transistor. You can do so many more things. Okay. So whatever you could do with these fellows in vacuum, through application of electric field and magnetic field. The basic flow is because of electric field. You're controlling it because of magnetic field. Okay. It's a very important subject. Okay. Have you heard a book called Parker Smith and Parker Smith? The teachers know, but any student knows. There's a book called Parker Smith and Parker Smith. Have you ever seen the book? No. You should ask them to buy that at least in the library, but not they may see that. The title of the book is called Problems in Electrical Engineering. The title of the book is Problems in Electrical Engineering. The book will be very only this small, like your diary. You have your typical diary, right? Take this. The book will be somewhat, take a little thicker than that. You have seen that, no? In IISc, somebody showed you that book. That is one place where a lot of jobless people are still there. So they would have shown you. Okay. This Problems in Electrical Engineering by Parker Smith, and one is father and one is son or something like that. They simply compiled the problems over a few decades. The problems all came from field. And they converted that into academic problems for students. Okay. And that book, nothing. It has only problems. It may have about 30, 40 chapters. Electric circuit, magnetic circuit, capacitance, electric field, right? And later chapters will be like DC motor, like induction motor, induction generator, synchronous motor. Many chapters will be there. So my take on every chapter will be 40 chapters. Each chapter may have about, let's say, 30, 40 problems or 50, 60 problems. So thousands of problems are there in the book. My personal take, which I still think is valid, is if you can solve 100 problems from Parker Smith, out of thousands, a few thousands of problems, if you can solve 100 problem, any chapter, any problem, your choice, I will say you deserve your degree. You deserve your electrical engineering degree. Electrical triple E, I don't make a big difference between them. Okay, you will deserve the degree. Very small book, but now AI will give you all the answer. You feed it to that. That's not what I'm saying. That means somebody knows. That is what AI is reproducing. You should know. That is the idea. Calculator is there. Have you stopped doing mathematics? What is 4 plus 3? You're not using calculator, right? That was because calculator was not given to you until 12th standard. If they had given you the calculator in 1st standard, 4 plus 3, calculate law. So you should not use something unnecessarily where it should not be used. Many students started using software tools, solving step response of circuit, step response of second order circuit, Bode plot of first order system, second order system. Okay, frequency response of amplifier. All this software. What do you do? Enter one detail like some transfer function, polynomial, something. Software gives you a plot. कर दिया सर हमने. What have you understood? If you solve that, it is less to your credit. It is more to the credit of the people who have written the software. There is a lot of physics and mathematics that have gone into the software, and people have done that coding. 99.9% is their credit. 0.1% is what is yours. Where it becomes useful to you is where you can do it faster, where you can include complications. Second order solution I should solve myself. 8th order I should use a software. If a 5th order system I am reducing to second order and solving, I should see what is the deviation if it is really 5th order. That I should use a software. You get my point? Software is not for those people who can't do the calculation. Who can do the calculation? Who know how to do that? But only do it better. Do it faster, more accurately. That is when it comes. I can't solve a second order circuit. Software kar dega sir. Better don't do that. You should know how to solve. The only thing it can solve faster. You want 100 sets of parameters. You will go mad doing this. But the software can do that for you, computer for that. You understand? So there is always a place where to use that. Kitchen knife is very useful. Correct? Without that your mother can't cook. Will you give a kitchen knife to a 1-year-old kid? Will you give a kitchen knife to a 1-year-old kid? Sometimes we do stupid things like that in the education now. This is conventional wisdom. Nobody has to tell you that 1-year-old kid should not be given a kitchen knife. Not to say that kitchen knife is not useful. If it is not there, we will not get our food today. We always have the wisdom when is the tool becomes your useful tool and when it could be dangerous to you, not so useful to you. This is why they said up to 12th, don't use calculator. That is why still in the country, people can add 17 plus 13 and say it is 30. I have come across young people in other countries who could not add this. 17 plus 13. Oh, I'm sorry. Okay. So no matter what all, our value isn't adding to our value. I'm worried about my value. I'm not undervaluing some tool. Okay. See here, what are we now doing is, in all these cases, now we are going into that semiconductor, like this complete this valve, and we are realizing one by one. So now this was a vacuum electronic. Now I have come up with an equivalent for that. Now this equivalent is made of semiconductor. What semiconductor? Neither conductor nor insulator. So insulator also I told you, don't get carried away by the term insulator. See, many of these are missed out. That's why it's being recorded. Insulator being insulator could be misleading. But insulator means what? By definition, it will not conduct. No, it conducts. When dV by dt is high, it conducts. When high frequency flows through, it conducts. Why? Why? The insulator is after all a dielectric. After all, dielectric. And the two edges of the dielectric is almost like a capacitor. And when will current flow through a capacitor? When will current flow through a capacitor? What is the equation for current through a capacitor? C into dV by dt. When the voltage across capacitor changes, it will go through that. That's all. That is why electromagnetic emission is there. All the problems are there. These problems are not so complicated. It's advanced topics. Basic electrical engineering. The solution lies in basic electrical engineering. You get that? Now this is semiconductor. Semiconductor again, intrinsic and extrinsic are different. You put p-type dopants into the n-type dopants and you create a p-n junction. This p-n junction is a functional equivalent of the original diode. Two chemical electrode. Electrode itself means electric potential is applied there. There's electric field there. Very different story. This is a functional equivalent. Semiconductor based functional equivalent. So we evolved a lot of semiconductor based functional equivalent and we started calling this as vacuum electronics and this as not semiconductor, but there's another thing called solid state. Solid state. Have you heard the term called solid state? Maybe the old courses in colleges called solid state drives. Okay. So this is solid state television. Some of you might have heard this, depending on your age group. There is something called solid state electronics. Now, this you can remove. You can call the solid state. Sorry about the poor handwriting there. Eventually,
Srividya, please mute yourself.
Hmm. The better that you draw is clearer for you. You have not done your own version of it. You have only copied what there was there on the board. When you do something, what is the next step? From here, I also want you to go towards an electric field. You haven't done anything? Why don't you do? This is a workshop. What does this mark here and there mean? I don't see where the charges are, no? I don't see where the charges are. See, next I want to understand the electric field here. Okay. I want to understand the electric field here. So it is better that you show me where the charges are or something like that. Where is your version of that PN junction? See, many of you are being tentative. Okay, please don't be tentative. Whatever you think is the picture, draw the picture. Otherwise, you will never correct yourself. Somebody asks me, what is this madam's name? I'll say Kamala. Rather than being confused, and somebody will say, no, she's not Kamala, she's Kavita. You understand? But we say, no, yeah, you know, I won't get a chance to correct myself. So please commit to yourself by putting it on that. Okay. Depletion charges. E minus HP means what? Electron hole pairs. Okay. I'm having a new challenge here. See, what is my point? I want to look at the electric field that is inside that. Originally, where did we come from? We came from vacuum electronics. We came from diode, two-terminal device. One negative voltage, one positive voltage, all inside vacuum. Right? And there was an electric field there. Because of that, it was working. Correct? Now, somehow, some material scientist, some physicist, some chemist, somebody said something. Fortunately, we have been able to come with a functional equivalent of that. I won't call this actually, electrical or electronic innovation. It is more a material innovation. You should be fair, correct? Yes or no? The original vacuum diode was an electrical engineer's innovation. This is more riding on material science development. Do you agree? I am honest. I will give more credit to material engineer than to any electrical or electronic engineer for this. Fine? But now I want to understand the electric fields in this. You get my point? So I have to put this up in a proper manner that I can start understanding electric field. You get my question? Is my purpose becoming clearer? The moment I say diode, I have to put my next question. What is that I want to understand in a diode? I want to understand, are there electric fields in a diode? How strong are they? Where are the electric fields? You get my question? That is a question because there the electric field created the diode. Here the diode, you are saying some depletion layer, something is there, but I don't know whether an electric field is getting created. Where is it created? How strong? Which direction? I have to ask. Question clear? Rather. Can anybody come up with something better for that? I also agree that there are three portions. There is a P portion. And these holes, what is the difference between these holes and these holes here? They are free. They are free. Here also they are free. When free means what will happen? When you apply some electric field, they will move. And what happens in between? They are somehow bound. They are somehow bound. But the bound ones, do they have charge? Do they have charge? Yes or no? Yes or no? Huh? No. They have no charge. Neutralized. No charge there. This is because you are reproducing the figure from some stage. You are reproducing this from some stage. A depletion layer, granted. Image file being reproduced. And something has got corrupted. Possibly. You have to say, why is a depletion layer getting formed? Why is a depletion layer getting formed? There's some layer. Left side of the layer, holes are there. Right side of the layer, electrons are there. So what will happen? Some holes will go this side. Some electrons will come this side. What is the result? Neutral or their bound charges? You're saying neutral. So can you clear that? Now first you draw P and N only before the so-called formation of depletion layer. Then you tell yourself how the depletion layer is. Clear that point and see whether there are charges inside the depletion layer or no charges inside the depletion layer. And say what the charges are. Go ahead. In fact, if you say there are no charges at all, everything is neutralized, there is no electric field. And somebody told me, oh yeah, in electronics we studied electric fields and all that. You can't deny because we can go back to the video recording. So put your P and N. What do you know about P? Excess of holes are there. N, excess of electrons are there. So start with common sense. These fellows go to that side. Those fellows come to this side. And after that, what happens? So have a clearer description of the depletion layer. Their immobile is all right. Are they charged? Are they not charged? What is the polarity of the charge? Which side is positive? Which side is negative? You come and draw. You come and draw. See, I need not have to ask. Sometimes you draw just this one. Voltage will come to later. Yeah. You can volunteer. It's not that I have to ask you. That's an expert drawing. Yes. Yeah, you don't have to waste too much on time on the right and the left, but I'm more interested in the middle. Yeah. Yeah. Very good. Okay. Is this correct or incorrect? Do you agree or is this better than the previous picture? Yes? So now you know what we want. So there are charges in between or there are no charges in between? Charges in between. Correct. It is the depletion layer as what are immobile. Yes. Have you heard something called interturn short circuit? Have you heard something called interturn short circuit? Yes. What is that? Huh? In an inductor or a transformer or some other machine, there will be two neighboring turns. They'll get shorted. So what will happen? There will be some arcing, unwanted current flow, and the exact device won't work that way. Why am I saying this? A classroom can have interturn short circuit. A classroom should not have interturn short circuit. What do you mean by interturn short circuit in a classroom? Okay, put up your hand. Tell your point. Don't be worried. Okay, don't be worried. If I extend my previous statements, I would encourage certain sense of shamelessness to learn. A child learns very fast. A 40-year-old learns very slow. What is the reason? Child does nothing. Bring a child to Goa. The child will pick up the local language in a few weeks. A 60-year-old person won't pick up the local language even after 6 months. Is that right or wrong? Why is it like that? One is the child's brain is active. That's one part of that. And And if you look at it behaviorally, child doesn't shy away from making a mistake. It gets corrected and learns quickly. Okay. Unless you're like a child, you're not going to learn. So put up your hand whenever you want, just and ask a question. And he has got a microphone also, so you can speak on that. And otherwise, I will repeat that. See, the microphone is there. It is right at the middle. Okay, he's showing the microphone. You can pick up. I'll encourage that. Now, is this picture correct? Is this picture correct? Right? We agree. So let me reason it out. Let me reason it out. Or can I ask some of you to reason it out? Why he has drawn like that? Huh? Can somebody come and reason it out? Why he has drawn like that? Raise your hand. Put up some volunteer. That lady at the corner. Come. Please. See, I am continuing to volunteer you. So the online audience also, I am blind to you. So you can, put up a hand or something and somebody is watching and you can raise a question, raise a point. Madam, please come. Okay, give me the reasoning for why he is correct. Yeah, please come a little faster. That will also make your blood circulate a little better. Go closer, yeah, and speak to them. Why that is correct? What is happening?
Initially, this was holes, and that was negative electrons. And
so this had a lot of free holes, and this is a lot of free electrons. Okay.
And then, as unlike charges attracts, here we'll get a layer, and then some of this excess holes will go there, and some of those excess electrons will come here, and then finally we'll get a diffusion.
So, but the left side is all negative charge, the right side is all positive charge. You agree with that?
Yeah. Yeah.
Okay, is that correct? No. Okay, go back. I think you can come and explain. Or you can re-explain, doesn't matter. Thank you. Give the microphone to him and you can go back to your seat. Yeah.
To the right are negative and to the left are positive, the holes. It was told in the other way around.
Come again?
No, to the left hand side there are holes which are positively charged. The right hand side there are electrons which are negatively charged. So it was said the other way around. So I was speaking about that.
Yeah, that is what I want to be clear about, because before knowing, I want to know this. So these are free holes and free electrons. Here it is negative and positive here, or positive and negative here. Huh? This is correct or incorrect?
Yeah, that is correct. That is correct. Yeah.
Okay. Fine. Now I want the class to vote. How many of you think is reasonably correct? Raise your hand. So most of you think it's correct. This is where I actually wanted to start that. I wanted to have reached this in a minute. Okay. So this tells why many times in the class it takes a little longer. Is this a representation of a diode or is this an actual diode? My question is clear. My questions always come from what is not there in the book. You will not find them in the end of the chapter exercise. Is this a representation of a diode or is it an actual diode? Huh? It is a representation of a diode. Okay. How many of you say that this is only a representation of the diode? Everybody agrees that what that lady draw was a representation of diode. It's a symbol of a diode. But this still is only a representation of the diode, or rather a representation of a PN junction and not the actual PN junction. If you agree with this, raise your hand. So not many of you think. How many of you think this is how a real diode looks like? Raise your hands. Okay, raise your hand, clear. Very good. You are the lone man to think that that's how it is. Can you give some argument why this could be a real diode? You give him the microphone.
That is electron rich part and for electron deficiency, and so
Correct.
basically there is a field that electrons moves in the opposite directions, and then due to that there will be like when electrons moves there will be another electric field that appears, which makes the electric field almost zero in the like junction part, so no more electrons can flow, and thus the junctions forms.
Okay, I agree with the junction getting formed, right? But is this how a real diode will look like? or this is still only a representation of a PN junction? That's the question.
Probably this is how it looks like.
This is how it looks. Thank you. Thank you for saying that. Other than him, most other people are not saying anything about this. So why do you think this is not a representative of the actual diode, if someone thinks so? Huh? Oh? Source must be connected. That is okay. If I take a picture of that inside, this is how it is going to look like. Can I say like that? No. Shashwat, go ahead.
There is no holes actually. It's a deficient of electrons is represented as holes. So like actually if you open a PN junction here, there'll be no holes.
Got it. But some material is being represented that way. I'm fine with that.
Yes.
Okay. Particularly, I'm saying that let us say the depletion. Like, can this really look like that? I think my question has to be driven a little harder. How do you think the actual diode looks like? May I pose the question like that? I was first asking whether this is a representation of a PN junction diode or does it how a diode look like? Okay, I'm not able to asking a different question. How does an actual PN junction diode look like? Huh? Very small. Oh no, but if I take a sectional view, I can only enlarge it 100 times and I can draw that. How will it look like? Huh? It is not that symmetrical. Okay, how will it look like? You come. What's your name? I forgot your name. Come. Yeah. Yeah, draw. How you think the actual diode will look like? Draw it at the top. Yes. Okay. Yeah, here. This man does something. See? Okay. Very good. Okay, that's the depletion layer, huh? Come again? Okay. The only thing is, many of you are metallurgists, engineers, but I'm just a lay technician. Okay. So I'm asking a question that way. Is it really, can I say, let's say I'm going to this, can this be the boundary of the diode? Huh? Is my question now clear to you? Where it has started from? Can this be the boundary of the diode? Yes, no. Only two answers are possible. No. How many say no? Raise your hands. Okay. It's roughly about 7, 8. Okay. How many say yes? Raise your hands. Nota is not permitted in this election. This election commission has no nota. Universal voting right, universal franchise, responsibility, 100% mandatory. You will be taken in a wheelchair to the polling booth if necessary to make you cast your vote. Right? Rules being told again. How many say yes, that can be the boundary of the diode? Raise your hands. That's the real boundary of where the device is. How many of you say that cannot be the real boundary of the device? The poll percentage is better, but still there are abstainers. Like abstaining from lunch and eating something, you cannot abstain here, more difficult. Yeah. Why are there abstainers? So what is your confusion? Is the question at least clear? Is it really like a brick where it is like this? Or it is not like that? There is no third option. You may have your confusion, but there's no third option. Yes, no. PC Sriraj. Yes. No. What is that? I don't know. That's the answer. No. Preferable choice. That's not given to you. You have to err on one of the side. Okay. Why am I even raising this question? So what do you do in that case? That could be the boundary of the diode, and that cannot be the boundary of the diode. What are that? Both are possible at this stage. So this is what we normally call as hypothesis. I'm saying yes, that could be the boundary. Then I will go further and I'll check that out. Something will prove that this is incorrect. Then I'll say, oh, that cannot be the boundary. Or I'll go ahead with that is that something will confirm or outside. The process is clear to you? Process is clear to you? Okay. So now I'm assuming that that can be the boundary. You understand? I'm the yes voter. Only 1 or 2 voted yes here, and maybe 10, 15 voted no. Nota again, illegal nota. Many are here. Next round, that won't be permitted at all. I'll come and raise your hand. Okay. So I'm saying yes. That is my hypothesis. Need not be correct. I'm telling myself yes. That is how it is possibly in a real diode. Okay. Now what happens if that is the case? What happens in the case? What are these? Charges? They are charged particle or uncharged particle here? Huh? This is an old technique of students. 30 years, 35 years back, I was a student like you. We used to sit in a class. We had a professor who used to ask a question. If we increase the voltage, then the flux, the answer has to be increases or decreases, right? What do you say? Creases. Creases. Don't say decreases or increases, right? Current increases, so the flux creases. It is for the professor to put in or dick before that. Don't think you have invented. Generations of students have been very, very innovative. Okay, when the charges are like this, are they charges or not charges? Still, I am not seeing clarity here. In the depletion layer, do we have charges or no charges? Huh? Huh? They are immobile. First, let us clear. They are all immobile. We agree? How many of you say immobile charges are there in the depletion layer? Raise your hand. Okay. What do you mean by this immobility? Somebody has broken its leg. What does immobility mean? Bounded by that. Okay. Some other way of putting that in? There is no, okay. Mobility itself is actually a term. Okay. We'll come to that. So it is immobile. Immobile meaning they are not going to move. Left side and the right side, there are free holes, free electrons. This is a p-type conductor, that is an n-type semiconductor. Clear? Now they are immobile inside. Are they charged and immobile or they are uncharged and immobile? They are charged and immobile. So the charge is there. If there is a charge, what will be in the vicinity of the charge? If there is a charge, okay, there is a positive charge. Nowhere else a separate positive charge will be there. Only in a physics textbook it will be there. It is impossible to create that. But that is created to ensure that you learn. If this charge is there, what will be there in its vicinity? Electric field. How will the electric field be? Right? There is some other charge. What will be in the vicinity? Very good. Oh, I know why NIT's AAA department is very good. So when there is a charge, there has to be an electric field around the charge. What was the definition of magnetic field your teacher told you? When did you study magnet? Huh? Magnetic field. When did you first read magnetic field in school? Physics. Thankfully, you're not telling that you studied only in the PMSM class. Okay. And machines only that taught you. You knew magnets in school only, right? And what did they say is a magnetic field? Huh? Don't say B vector and H vector. Huh? Lines, okay. You would have drawn the magnetic lines. What do you mean by magnetic field? If somebody asks you a simple definition, magnetic field is a known term, right? Correct. That field, is it like football field? Paddy field. But this is also field. You understand different usages of the term? And it's called magnetic field. So what is the definition of a magnetic field? Huh? Huh? If you keep a magnetic, so you will experience some force in that region. Okay, then? Huh? Region, which region? We are feeling the force, okay? And where will you feel that force? It's because of what? Huh? Okay, I'll tell you what my teacher said. The region around a magnet where you can feel the effect of the magnet is magnetic field. This is what I remember my science teacher telling me. This is right or wrong? At least at that point where I know only a magnet is a bar magnet, this is what it is. If I keep some iron piece here, it will not attract. If that iron piece comes to the tuck. Region of space around a magnet where you can feel the effect of the magnet is magnetic field. At that level, it is fine. At least that definition is necessary. So there is a magnetic field. Correct. What is the electrical equivalent? What is the electrical equivalent? The region of space where you can feel the effect of where you can feel the effect of charge is that. Right? Now the charges are here. The charges are here. What will happen here? What will happen here? Effect of charge. There will be effect of charges. What will be the effect of the charge? Electric field. And by default, what is around the diode? You are not working in space. You are in Goa. So what is there? Matter is there. Electric field is there. Is this immersed in oil? The diode. It's air. What will happen to the air? Ionized. Air will get ionized is not the first time we are saying this. We said that sometime back. Did we say? When did we say that? Huh? I had that in mind. When we did the electrode, I said thermionic emission. Somebody ready. Then I said anode. Somebody ready to collect. But these are not the only players. There are several players. You have to remove the other players. That is why you have to have vacuum. You understand? That statement was also to prime you to the fact to see this here. Okay. The air will get ionized. The air will get ionized. You should need some material which will make sure that the electric field does not go outside. Okay. So my hypothesis is incorrect. What is my hypothesis? That is how the diode looks like. Okay. How many of you have seen an electrical machine? Raise your hand. See, Professor Soumitra is not raising because he thinks that you will see him and then follow that. So he doesn't want to give you that safer option. Okay. So don't follow some of the faculty in this because they want you to think freely. But the rest of you have to do that. So all of you have seen. Is there a magnetic field inside a machine? Yes. Is there a magnetic field outside a machine? Huh? Yes or no? Huh? Very less. Why is it very less? There is a yoke around that. That is highly permeable that contains all the magnetic field inside. So the magnetic field should not come outside. Have you gone to hospital? There is a radiology department. Have you know that? Correct? They will not let you near the radiology department. freely. Like OPD, you will walk. Radiology, you cannot walk, right? Why? Of course, radiation hazards are there. What are the known radiations for you? X-ray. There is another kind of scan, modern scan. What is that? MRI. What happens in MRI? High magnetic field is applied. Somebody who went with a cylinder near that got sucked into the MRI. Suck. Why should you not go near a magnetic field? Why should you not go near a magnetic field? Huh? Huh? Ah. This magnet will disturb the current. They will think I'm a little cranky. Even today they think so. What is the problem? What is the problem? Even more serious than that. He says human body has current. This current will be disturbed when you get the magnetic field. I appreciate that sense. You know that, okay, current flow is going to be affected by some magnetic field. I'm grateful to that. But there is something even more. Okay, magnetic field influences what kind of material most? Magnetic materials. Are there, what is an example of a magnetic material? Metal, which metal? Is iron inside your body? Where is that? So you should be exposed to very, very, very minimal amount of fields. That's a safety requirement. We really don't know what they are. Let us be honest about it. There is so many phones and so many things, right? There is a lot of electromagnetic field. We don't know. Those things called house sparrows vanished. And they said that is because of this. We don't know what are the effects. You understand? Because what is in the human body is not the result of only one thing. It may take us several decades even to understand what is the effect. So let's be honest about what we know, what we don't know. Still, they think that there is nothing to suggest that there is going to be something that is harming you. And within some levels, and they are permitting some levels. You understand? Many times the regulations will come much later. We don't know after knowledge builds up. But we should know this basic that magnetic field should not come out. The same way electric field can also ionize air around that. So the electric field and magnetic field have to be contained well inside a device that you built. They have to be contained well inside a device, and they should not be there outside. Okay, the deviations are like wireless power transfer. But you have to be very careful about them. You have to be very careful about them. You don't have to worry when current is flowing through a conductor and there's an insulator around that. But when there's wireless power transfer, yes, the safety needs to be at a higher level. Okay. So that's what I'm trying to say. Now this magnetic field has to be contained in electric field. So electric field cannot go outside. Other example is, let's say heart is there. Where are your critical body parts? Heart, lungs, kidney. Has God given you, okay, I will carry my heart in my left hand and lungs in my right hand and I'll walk. Has nature made us like that? They are deep inside, right? So in rough equivalence to that, high magnetic fields and electric fields have to be contained well inside the device you build. They should not be coming outside that. This is a violation. This is a violation. This cannot be a diode. This cannot be a clear. This is only to say that. See, I don't want to be stuck there. That is my problem. I don't know. I don't raise a question. Firstly, I don't think. Therefore, I don't raise a question. And when I raise a question, I don't want to commit. Okay? All these are we have to overcome. We came to this answer only. We committed ourselves to a wrong answer. We committed ourselves to a wrong answer. Later proved that that has a consequence that is not acceptable, and therefore this cannot be the correct answer. You understand my point? This will not happen if you don't commit to the wrong answer. So there is a reason to commit to a wrong answer too. Clear? Okay. Now how does the diode look like? Does anybody have an idea? The packaging part. Correct. How is it packaged? Does anybody know? I've also become smart. Yeah. How is the diode built? So what is the fact? We know as a layman, electric field should not be exposed outside. Where is the electric field? It is near the PN junction. So the PN junction should not be visible from outside. You understand? That is how it is created. Okay. Now, I'm telling a procedure not as a device manufacturer, but I'm going to use my lay sense. Okay. As a general engineer, as a general person who knows some physics, maths, some common sense, I'm going to come up with a procedure how I can do that. Okay. What I'm going to do, I'll take some material. I'll call this as N-type material. I'll call this as N-type material. The long material. This is a broken line. Now I want to create a PN junction. I'm thinking how to do that. I'm thinking how to do that. How do I do that? Bring some PN, push them inside. Hey, andar chalo yaar, andar chalo yaar. This is the door you get in. How do I introduce P into this? Think of that as a common person. The entire microfabrication and all that are much bigger evaluation from that. How do I do the doping, Kanna? This is already doped. Now I have to create a PN junction. Put that material, heat it up. So how will you heat up? It will go inside. So if it goes from multiple directions, then it will be neither a P material nor an N material. Correct? It has to come from somewhere. You entered into the classroom not through the wall, either this door or that door. Okay. So let me think through that. If I heat up, what will happen? This will become, that is an insulating layer. Correct? When I allow path, what do I do? There is wall here, right? Then doors are created. You understand? No, this is like wall. Then can I create a door? How do I do that? Let's say this region, I open out. This region, I'm opening out. I'm opening out this region. Is my picture clear to you? So the dashed portion is removed away. Now what do I do? Let me redraw that. I'm sorry, I should not have. Eraser. Okay. Eraser has to become a pointer. Pen. Okay. Please put up with my bad drawing. This is N, and there is a hole now. Now I inject something. That has P-type dopants. So now what will happen? This fellow will come and settle down. So that side will become P. This side will become N. So that is where the junction. If I pump further, what are those lines? PN junction. Those lines are the PN junction. Now that PN junction is not exposed. This is not exposed. So one big challenge is to decide on the speed and other things. It's very difficult. Okay, because you don't know where you are. This you should have even come much later, right? But the idea of depletion layer, takes us longer now. So that's a hazard, like an unpredictable traffic. In my class also, you cannot say what is understood, what is not understood. So this is now a more realistic PN junction diode. You take Cedra and Smith, okay, for example, and quite a few of that I will be like that. Okay. For example, if you take Cedra and Smith, they'll show you a picture how it looks like. Okay, that was only a representative. Okay. But is it correct to represent it like that? Is my question clear? See, the story never ends. This is what? This is how a realistic PN junction. How do I confirm that? Open up a book and see. Now you have got an idea. The book will tell you the details. You get my point? But unless you open your brain, the book will not push ideas into your head. This is that. Even if you get a bit of yawning, this is necessary to open. You know why you yawn? What happens when you yawn? Huh? Goes to? Oxygen level goes to? Reduces or goes up? By yawning, more oxygen goes where? Supposed to your brain. So it basically means your brains are inactive. So how do you make your brain active? How do you make brain active? Chemically, they'll have tea, but that's a chemical method. Physically, just exercise. You stand at one place and jump 20 times. Blood starts circulating. Initially, they may think you are a little crazy, but that doesn't matter because if your brain works better, it's good for you. How many of us are not doing crazy things, right? If nobody's ever been doing crazy thing, the world will be very different. Huh? Bulls. Okay. Some other time I'll tell you. From the time you wake up, in less than 10 minutes, your body and mind can be ready. Less than 10 minutes, your body and mind can be ready for the most serious lecture, research, simulation, experiment, whatever. 10 minutes. Okay, think about that again. Director has said we should discuss over coffee. So I will keep that during the time. So you can read this, and this is also a text that I would recommend for basic electronics. Some of these that I cover may also will come from this. So this is how a realistic one looks like. Now my offense is, why are you fooling us with this picture? Why are you fooling us with this picture? That reaction should come. If this is correct, what is that? That's also given in book, right? Why does nobody think like that? The moment I say these two, this fellow is better, you must say, why not this fellow? Correct? Get me? Why is that picture given everywhere? Huh? It is easier to represent, but easier to represent does not mean that I can do whatever you want. What is your name? Yash. I can't draw something like that and call that Yash. Right? Something. You know how great my writing is. If I draw how it's going to look like, right? You know that very well. And I'm going to draw that. See, he knows how it will be. And I will say this is Yash. The professor in IIT Kharagpur told us, okay, when about drawing, if you know to draw, you will draw a horse and you won't write a horse. If you don't know how to draw, you have to draw and write below that a horse. So if I draw, it won't look like Yash. I will say it is Yash. Then you will have to be kind enough to agree that that is Yash. Okay, so that is how that is going to be now. But so representation doesn't mean anything and everything. How do people shown in Microsoft Teams and meeting and all? One circle and two lines. Means what? Person. One circle, two lines. Right? That represents a person. That can be Yash, and that can be someone, that can be this. So many Kirti, Kriti, it doesn't matter. But that's representative at some level where you are not worried about who that is. There's a next level. Even if it is a representation, it should be acceptable. You understand my point? It should have a meaning, what it is meant for. Okay. Will an aircraft carrier, pilot, be worried about how Yash appears? Whether his hair is like this or like this, will they worry about that? Right? Not worry about that. What will the pilot or the person responsible for flying the aircraft worry about as far as Yash is concerned? Huh? Body weight. Body weight. And he is human. He needs a lot of oxygen and body weight. What will be the air hostess would be worried about? Huh? Whether he is veg, he is ordered food, That is veg. That is another level. He is a very nice gentleman. You'll not be worried about that. Yeah. Attitude. Yeah, I think everybody else is here is having very good attitude. So our hostess will not be worried about that. She'll be worried, or he will be worried about whether you have to serve you veg food, Jain food, this, that, or you have ordered food at all. That is what their concern is. So everybody has a specific concern. There's a specific reasoning. What matters to us is passenger number 32, seat number 32A needs to be served Jain meal. 32B has to be served veg meal. 32D has to be served this meal. You understand? So everybody's things goes like that. Now there must be a reason. Even if I'm going to represent it like this, there should be a reason for representing, and there should be a justification for representing. What is the reason? One way to say, I want to simplify. Doesn't mean it is like my drawing some random thing and calling it Yash. That's not going to work. I'll draw some random color, this is Gaurav. Not going to work. So why is it justified? Unfortunately, we are going slower, but I think it's better that we do that. Why is it justified? Because these are questions for which answers are not there in the books. And this is where you have to think. Why is it justified? Just because I cannot draw his picture, I can draw what I want and call it him. What's your name? Siddhan. Siddhant, not Siddharth, he's Siddhant. Very good. Right? What is the justification? Okay, when I don't know what is the justification, then I start questioning what could be a justification. You understand my point? What could be a justification? And what could be a justification? Every answer that I give is a hypothesis. I'm going to verify. Right, wrong. Luckily, I may get something right. Something can go wrong. So I'm moving it slightly. What could be a reason for that representation? But that representation is correct. It is there in so many books. His books will not be published. So what could be a reason? What could be a reason? Shefali, you want to try? No, what could be a justification for this kind of a representation? Well, this is a reality. Correct. No, but still, I told you, that that's not correct because there are charges here. There are charges here. So there are more of those positive fellows are here, right? More of those, some positive fellows are sitting here, immobile, right? Sorry. Maybe some immobile fellows are sitting here. And we said these charges are close to air, external air. They are going to ionize. Therefore, it is not correct. Yes? Still, what is the reason this is there in the books? Okay, one way to see that is a physical system. Madam, solunga. Okay. So there are always two things. Let's slightly generalize. There is a physical entity and there is a model. There is a physical entity and there is a model. That's what I was trying to. The model, as far as Yash is concerned to a pilot, is his body weight is so many kgs. His model, as far as a cabin crew is concerned, he is a well-behaved person who will have a vegetarian meal. I'm taking care of Shashwat's concern. You understand? Their purpose matters. Their purpose matters. Okay. And there's something that has to be. So there is a model. And the model to a particular physical entity is not unique. The same physical entity can have multiple models. Depends on the reason why it is necessary, the purpose it is necessary, and the model should be justifiable. The model will not be the exact physical system. The model will approximate something, will assume something, ignore something. But it will be valid for that purpose. That is why it is a model. Okay. So the middle figure that we have shown can be taken as a physical entity. That is how diode looks like that. And the right hand side is a model. I don't know the justification, but it is a valid model. It should be a valid model. That is why people are accepting that. That is why otherwise it won't be there in book. It won't be there in physics textbook. It won't be there in electromagnetics book. It won't be in electronics book, right? So now I have to find out what should be the purpose, where it is valid, or why it is being justified. The purpose, what do you think is the purpose? We eventually want to understand it is a two-terminal device. Some of you tried saying this. I'm trying to make that more clear. This is your anode. This is your cathode. So this is a two-terminal device where there is certain voltage being applied here. There is, and because of that, some current will flow through this. You want to get a relation between the terminal quantities. You want to get that could be a purpose. My intention is not to exactly say, this is how exactly Yash looks, this is how exactly Kirti looks. But I'm going to take them like this. They are young people. When they are young people, at least olden days, they used to think young people don't need hospital facilities. The number of hospital beds per 1,000 in an academic campus will be very small compared to the number of hospital beds per 1,000 outside society, because here young people are living. Now things have changed. Where it matters, you're taking elderly people. If you're a tour organizer taking elderly people, you have to take a doctor or nurse with you. Right? Purpose matters. So to a tour organizer, the age matters. Here, I'm trying to put that hypothesis, suggest that into your mouth. Maybe we are trying to look at the voltage and the current relationship. Maybe. But so what? Still, that is not a justification. The purpose comes. Still, there has to be justification. What is most striking about this and that? I have drawn this on the board. So board is two-dimensional, but the actual device is three-dimensional. It could be a box, or you consider the straight line and spin that around. It could be a cylinder, right? But I am giving a 2D representation. Here, the drawing is 2D. The drawing is still 2D because I have drawn it on that sheet. But what is the information? What is the information here? So along this vertical line, am I considered anything about the vertical line? What is my assumption about this vertical line? Not able to crack this. This is a 2D picture. Clear? Correct? In reality, everything is 3D. 3D is represented as 2D because I have to draw it on a board. But you know it is 3D. Now the question is this 3D or 2D or 1D? Did you hear? It is 1D. It is 1D. So this is not coming from there. Looking at the pictures, I'm saying that because I'm not worried about the vertical direction. If I take any line like this, I think I don't have to worry about one point here and another point there. I think they are similar in some sense. The variation is only in the horizontal direction. Let me call that as X direction. So this is a one-dimensional representation. This is a one-dimensional. The vertical thing doesn't matter. If you have a point called P1 at the top, P2 exactly below that, we believe P1 and P2 are identical, similar. And if I have P1 and P1 dash exactly the direction normal to the board, they are similar. That is my understanding. That is why it is one-dimensional. It is one-dimensional. So why can it be one-dimensional? When can it be one-dimensional? When can it be one-dimensional? Let us say I have this PN junction. I have a point P here. And I have a point Q here. I have a point P and I have a point Q. Let me write down P and Q also here. I'm asking a question. What is the question? What is the charge density at P? What is the charge density at Q? What is the electric field at P? What is the electric field at Q? What is the current density at P? What is the current density at Q? All these questions can be asked, right? Whether they are equal or unequal. It depends on the normal distance between P and the PN junction and the normal distance between Q and PN junction. Okay. Right? This is a physical reality. Any property that I want to study in my actual diode, the property largely depends upon the normal distance between that point and the PN junction. Am I making sense? No. Yes, no. No, you didn't even hear me. When can the two-dimensional problem become a single-dimensional problem? Here the PN junction is the reference. If I can tell the property of a particular point, mainly in terms of the normal distance between the PN junction and the point, then it is one-dimensional problem. You get me? Here if I say P and Q are equidistant and their values are equal. Now I'm saying P has a normal distance, Q has a normal distance, and they are equal because I want to start with simpler case. And I see that if they're equal, the electric fields there are equal. Their charge densities are equal, or J is equal, or whatever variable or parameter that I'm looking at, they're equal. So that variable or parameter depends largely on the normal distance of the point from the PN junction. You understand? It is not that all these are not discussed, all these are buried. And like that boy was asking, why should we study? Every generation thinks that they know very well. And all this is glossed over. And the result is we are actually sitting on some bubble of ignorance. And we don't know when that will hurt us. So you have to, that troubles me is that when I say this is correct after a lot of argument, then you should say that why is it being given that in the book? If this is right, that should not be there in the book. You understand my point? Yes, that is my message to the students. If there is one warning, then that is the warning. When there is an apparent contradiction, you are not even noticing it. Am I right? You are not even noticing it. We have to notice, point that out. Question. Whether you question yourself or your neighbor or your teacher is another point. So, here what happens is, if I chase some other point, okay, if I take some other point, let me call this as, sorry, this is a little farther. Let me call this as a point R. Let me call this as a point R. Now, this R will be different from P and Q because it has a normal distance. The situation is that in an actual diode, okay, any property that I want to study, what are all the properties I would like to study in the diode? Because I'm putting that. What are the properties I would like to study at any particular point? These are properties at a point. So that the charge density is one possibility. Then current density is one possibility. Electric field is one possibility. These are all properties defined at point level. If I have to study it at a point, I can simply study it in terms of normal distance between the point and the layer, PN junction. Then it reduces into a single dimensional problem. And that is not always correct. There will be something called edge effect and all that, where it changes, right? The PN junction will have a sudden change somewhere. There it will not be correct. But those are things that they have taken care of. Subject to all that, this is valid. You get me? And therefore, this is correct for a representational purpose. And here the basic assumption is the problem is one-dimensional. What is the dimension that matters? It is not X or it is not Y. It is a normal distance between the PN junction. If generations have been studying a diode and not recognizing this point, it's worrisome. Is that right? Okay, and therefore this is correct. Therefore, this is correct as a representation for only that particular purpose. So the task now is, this is correct. So we'll come back to this. Initially, there was a class had a confusion on whether the charges are mobile, immobile, but that was okay. Mostly said immobile, whether the charges are there or not. Some of you felt that there is no charge. Or, charge is there. Some felt, and some were non-committal. If you feel that there is no charge, it is all right. But being non-committal is a bigger mistake. It's being heavy. What's your name? No. Behind, yeah, left and behind you. No, between you. Is it heavy? Is it going okay? Okay. You were slightly in a tri-state mode from the way I could guess from your eyes. Now you have come to the active mode. You know what is a tri-state mode, right? The device won't respond to any signals. Okay. Tri-state buffer. Once it is in tri-state, chip select. There is a chip select signal. Only after the chip select, inputs will give the corresponding output. Without the chip select, no input will give any output. Okay. So this is now why it is like that. So we will use this now. Honestly, I wanted to have come to this point like around by 11 o'clock today, but it's all right. We will give ourselves a little time. So what we will do is now we will go by this single dimensional representation and use the single dimensional representation to first understand the charge distribution. That is obvious from there. From the charge distribution, we will look at the electric field distribution. Okay. And from the electric field distribution, we will understand the potential difference between 2 points. These are the steps I will do. Right? Not further. Then I'll say how the charges will look like at different conditions of the diode. It is not only the depletion region, right? When the diode is conducting, some charges will come and stick to them. Some charges will come and stick to them. How many of you have seen an electronics textbook of late? How many of you have seen an electronics textbook recently? Okay, long back. So I request, take your electronics textbook. We have 1 hour time, right? You can have your lunch. Please open an electronics textbook, physical, ebook, whatever. Look at the diode chapter. Look at the diode chapter and see the pictures of only, let us say, the charge density. Okay, look at only the pictures of charge density. Because that is our starting point. From the charge density, we are going to look at the electric field and then do this. Okay, so we'll do this and say what is the voltage. And from that point, we will take over to say, how can you make a diode that can stand high voltage? This is the actual point that has a power electronic relevance. So in an ideal situation, we should have come to this point very, very quickly. But let's not worry about that. This is supposed to be a workshop. We have to find out what all we are not doing correctly, that we don't repeat them. In a workshop, they'll see what is all not imperfect. In a showroom, they will show everything that is perfect. Right? In a workshop, they have to see what is all not clear. That's the basic purpose. Correct? So we'll do that. So we will do this now. And again, I will only give we will not derive IV of the diode, but we will look at how do you derive the IV. You need drift current and there is something called diffusion current. We will have to understand whether we understand this. Okay. That's all that we'll do it in a very important steps there to reach where and why there is you will see that the exponential distribution will be there. I will leave some of the questions to you. Only 2-3 of these important points were done. Okay. And then we'll have a exponential relationship between the voltage and current. Clear? That's what we'll do about a diode. The one important point we'll do is how can you create a diode that can handle high voltage. That is a very, very important point that will be covered by doing this. Then we'll use that characteristic and quickly go over to how do you can look at a BJT as a back-to-back diode and in active state, and how do you quickly go to the other states, and then we'll go to the MOSFET. So we are going much slower than that, but let's do that because let's do the basics of them, and then we'll go to the machine converter as we go forward. So I'm hoping that maybe in the afternoon, about half an hour, 45 minutes, if you come with at least some level of preparation, the diode we can go up to the high voltage diode. It can be maybe about 1 hour. And from the diode to the BJT, I want to take at least another half an hour. So about 1.5 hours, right? So the day will largely, MOSFET, I've always found it a little bit of a challenge. And actually what we have in power electronics is what is called as vertical MOSFET. I'm not even going to do that much. I'm only going to indicate what is vertical MOSFET. I'm going to look at a lateral MOSFET. Why does it look the way it does? Okay. So with that, I'll go into switching. I'll try to give you a difference between what is analog electronics, what is digital electronics, and what is power electronics. Okay. You may have MOSFET, you may have BJT, but how they are different in analog electronics, how MOSFETs are used in digital electronics, what happens to a MOSFET in power electronics. Clear? This will be a very, very fundamental as far as the power converters are concerned. And then we'll take it from that particular point. Okay. Yeah. The lunchtime is over. We'll come back on that. Yeah. Yeah, we can do that. NIT madam says we should not press hard and we should be fast. We should not stay in the same place. Combination of normal force and slow speed being low. Both are there. That is our hypothesis. We have to verify that. Ah. Give her a mic, no? Ah.
So like here, this is the P side and the N side. Then here it will be for this, here will be the majority charge carriers and here will be the minority charge carriers. And for N here, it will be like, again, majority charge carriers and here it will be the minority charge carrier. Then the concentration will somewhat, if we try to draw the diagram for this, then it will somewhat look like this. First it is positive, then positive and then negative, like this.
What concentration is this?
Charge carrier concentration, like here it is positive, so here it will be positive, and like this it will
and
be
the depletion
negative.
layer that is very thin in between.
Very very thin in between, like that.
Okay.
Yeah.
Now this is under what condition? It's a PN non-conducting open PN junction. Open PN junction.
Non-conducting.
Non-conducting. So when the PN
Yes.
junction conducts or something, there's a change around that.
There is like external field will be applied.
Correct.
Like this, conductive mode.
Does anything happen to the charge density on the two sides of the depletion layer?
Yes, like again, this depletion will reduce. Like if it is
Correct.
back.
I think you press that and then
Previous.
Previous.
Details. There. Very down.
No, it's not gone. Huh?
Yeah. Redo. Shall draw it.
Whatever you save it now. Session 1 you save it. Yes, you save that for session 1. Later we may not even have a memory to see what to. At least now we know. Huh? Okay, doesn't matter.
Session 1 and 2. No, session 3.
Yeah, okay, fine. I think you have done your job. Maybe yeah. Did you have anything else to show? The other content? Nothing. Okay, fine. Did anybody see the book? Is there any figure that is there? No. Huh? Didn't have time. Only had to go to the mess. Huh? Can't see a book, no? No. Okay. All right, let's see. This one, no? is chosen now. Pointer options. So I've chosen the pen. Okay. Successful now. Anyway, this is my depletion layer. This is my depletion layer. I'm drawing the depletion layer big. Because where is the electric field? The electric field are where the charges are. This is where the charges are there. So you will do this. Now, let us say I have some positive charges on this side. I have my positive charges on this side and negative charges on that side in the depletion layer. So I want to understand the electric field. Correct? This is a one-dimensional picture. So nothing changes along this direction. They are all equal. It is only in the horizontal direction. So I'm looking at this as a thing of x. This is what I'm calling as x. So now what I have is, I have a positive charge distribution here. This side, let us say, is positive. This side is negative. Okay. So Jayanti's formula. Previous one goes off. I don't know why. This is negative. The charges are like this. I want to visualize the field. Left of this, right of this, not concerned. There are free here, free there. Nothing is moving. This is open circuited or whatever. Or this can be shorted. There is no conduction. The reverse blocking, whatever. So it is like this. I want to understand the electric field. The question is clear to you, right? And the electric field is not a function in the y direction. The electric field is not a function in the y direction. The electric field is only a function along the x direction. And what will be the direction of electric field in this case? Positive charge, negative charge, horizontal. You are clear? Yes. Now I want to visualize. I want to visualize the electric field. Only when you visualize, there is some picture. It is difficult to eat food when we cannot visualize, right? We all know how is rice, how is roti and all that. You get some Chinese and Korean and serve something, they won't know what they are doing. And very seriously, when I was a school boy, I was in Mumbai. My uncle came back and he was narrating an interesting incident with a foreigner. So, sometimes in Mumbai, you are a little casual, there's a lot of rush. So you do things fast and you can't do that. So there's a place where people are given food and they eat in hand. Chapati is given and sabji is put onto that, some dry sabji. So what are you supposed to do? Hold it, just eat it and go. This gentleman ate all the vegetable and thought the chapati was a plate and threw it off. Right? This is a real life incident. So you need to know. You need to know that it is food that can be eaten and all this kind of stuff there. So no matter what, I first want a visualization of that. If I want to do that, I want to visualize how the fields are going to look like. I am not very happy with the plot. Somebody can tell me how the plot is going to look like. It will rise and fall, fall and rise. Okay, that is secondary to me. I want to visualize. How do I visualize? The question clear? Purpose, I want to visualize. Right? Why? You know. That is when I get a feel. That's when I'll be able to understand, do more complicated things later. How do I visualize? Huh? High at starting and where will it come and decrease? He says it is high somewhere and it decreases. I don't like this. He may be right or wrong. He may be right or wrong. get a picture of this. Why it's positive there, why it is negative here. Hmm. Hmm. Did you understand what he's saying? Huh? Did you understand? He didn't use a mic. Okay, I'll tell you. He relies on. Okay, give him a mic. Give him a mic.
Sir, so what potential means the amount of work done to bring up unit positive charge to the area. So it's
Potential definition. Unit positive charge is not a little clear from infinity, where the potential is 0 to a particular point P. That is the potential at T. That is the definition. Very good.
so at starting of the layer, it's positive charges are accumulated.
Yeah.
So we need to do more work. I mean, we need to do work to bring the charge because positive charges repel each other. But at the negative side, like positive charge and negative charge attract each other. So there's almost zero work done to bring the charge.
Is it right and wrong? What is right? What is wrong? So he is trying to bring a positive charge from infinity to here. He says bringing the positive charge here is most difficult for me. Okay. Therefore, this should have the highest potential or electric field. This should have the highest potential or electric field. Wait. How much is the energy that you have to spend in bringing a unit positive charge from infinity to that point? Correct. So you are saying it is difficult to bring that here. So a lot of work has to be done by the time it comes here. That means the potential at x is equal to 0 is high and not the electric field intensity. First. Next, you are saying it will go to 0. In fact, if it is there, you will not do work on that. Work will be done on that. In that case, the potential will be negative, not 0. You get my points? Clear? So, you are trying to develop a field, which is correct. You are developing a field in terms of the definition of potential. That's very good. So, but what you are missing is you are mixing up between potential and electric field. So, he says at x is equal to 0, the potential is highest. And he says on this side, the potential is 0. That's not correct. It might be potential is negative, is my point. So is it clear? Because bringing to the negative side here, you are not doing any work. Work is being done by those charges. They are attracting them. So the potential could well be negative. That is my point. So having answered his question on potential, in terms of potential, I am talking about the electric field. My question is, right, not this. Okay, so this is, we will remove this. Okay. Okay. So it is a decreasing function of potential with respect to x maybe. That is what you are saying. Now I'm looking at electric field. Question is back. How do I'm not even saying how will it vary like that. How do I visualize the electric field? How do I visualize the electric field? Why is it not apparent to me? I'll give you a counter example. Tell me 1 minute. I'll give you a counter example. Can you visualize the electric field here? Right? Correct? I'm able to readily visualize. I'm not able to visualize there. You get me? Yes? Here everybody immediately told me this. Now go ahead, Ma.
Sir, can we assume like this? There is one reference charge and the middle line, we can take it as a reference. So one charge we are bringing from infinity. So if we take middle line as the difference, then distance between both of them will get reduced and reduced. So electric field is inversely proportional to distance. So electric field will be maximum at the between. Like it will try to bring that. Since
Electric field will be maximum where?
in the middle, that is the junction.
The actual junction.
Here it will be maximum. So here it is positive. So one positive charge we are trying to bringing in. So this is middle line is the reference. So distance between both of them is getting reduced, and electric field is inverse of distance. So since distance is getting reduced, the electric field will be maximum there. And again, after that, if we move this side, again the distance is increasing. So then again, electric field will reduce in this way. So we'll get a triangular plot like that.
Very good. So she's saying that the electric field will fall like this.
Like this.
That is what she says. Is this right? What is your gut feeling? So nobody, are you able to confirm this? You can confirm this? Let us put that way. Don't forget, don't worry about who made this. This is a suggestion. Okay, this could be the case. We don't know whether this is the case yet. This could be the case. Correct? So you can agree in question. You should have a basis for both. You get me? So what are there any responses? Can you confirm that what she's saying is right? If you understood all her arguments and if you agreed with all her arguments, both are necessary, then you can say she is right. You get me? You should understand all her arguments. Sometimes that may not have happened. And you have to agree with that. I may understand but not agree with that. Only when I do both, I can confirm. Correct? Can anybody confirm this? You see, there is a logical process in everything. And I also did a small sample study, my informal talk. And a slightly side story, but I'll tell you this. Whenever you do any learning activity, in a course particularly, there is some kind of new learning that happens. Okay. So pedagogically, they'll try to see what are all they, how they are, etc. They normally put them in 3 buckets. They normally put them in 3 buckets. Okay. That is, there are many ways. Oh, sorry. In whatever you have learned, you might have learned some new concept. Then there is another layer where it is incremental. You know a good part of that, but something got pushed a little further. Something got pushed a little further. And there can be other things where it need not be new. It need not be farther. It can be a reorganization. There is a reorganization. Okay. All these are valuable. You will know many things, but you know that they can be connected differently. And something you know, but you pushed yourself a little farther. You applied it to this context, and some things you do differently. Whenever you do a pedagogical survey stating the outcomes, particularly with undergrads, they'll mostly be able to identify only the first one. They'll mostly be able to identify only the first one. You ask anybody what is the gain, what did you do at the end of a course? They'll mostly be able to tell only what is new. They did not know anything about that. But it doesn't mean that the other two are useless. It doesn't mean. The message I'm giving you is going down this is a question of maturity. Going down this is a question of maturity. Maturity in evaluating your own learning. Even a child, if a child doesn't know a fruit, madam gave some fruit today, there was some juice served, the lunch. I didn't know the fruit. So if you show the child this is a new fruit, or child say that, oh, I know banana, I know this, but this fruit is new to me. This is new. Even a child can recognize that that's a learning. Correct? I haven't seen a cashew fruit. Go ask a lot of them. Right? It's new. A child can recognize. But it is difficult to recognize that I knew something, but I've been able to extend that. Even more difficult to recognize that I have reorganized things internally. Okay, because now things sit much lighter in your head. Things sit much lighter in your head. It is more closer. So actually with maturity, this is the direction of maturity. You need maturity in evaluating yourself if you want to come down. And a good part of courses are really from bottom top. No course can ever start, right? Totally fresh ground. Every course has to pick up a lot of threads from the previous ones and go about doing it. If you do a power electronics course, there will be a reorganization of circuits. There will be reorganization of state space equations. There will be a reorganization of something else. There will be a reorganization of, depending on what kind of control taught to you, Bode plots. Many of these will get reorganized and reconnected. Some of them will be incremental. You know, oh, I can apply this differently now. And only some things will be new. Okay, so that's something that I just wanted to tell you here when you get in there now. So here, when you coming back to what she said here, she's saying this. Okay, so I posed this question to you. Do you agree? If you agree, there are two components to that. That is, I'm not even asking whether you're agreeing as an opinion, whether you can confirm this. You understand? Confirm means you are a technical person, you can confirm that it is right. I say 15 plus 13 is 22. Will you confirm? 15 plus 13 is 22. No, it's 28. Because you know arithmetic, you know addition. You are checking that. You are saying, oh, what is he saying? 15 plus 23, he's saying 22. Oh, no, that's not right. And you disagree with me. I say 15 plus 13 is 28. You confirm. You add, it's correct. So you understand what I'm saying. You agree with what I'm saying. Okay. So is anybody able to confirm? No. Now, are you able to understand what she said? What is the argument she was saying that why the field is highest at the middle? Very good. So, up to this, there are no charges at all. So, the electric field is practically zero. Here also, there are no charges at all. The electric field is practically zero. The point is, when you move from here, what happens? When you move from what happens? That is what is our approach. Okay. Still, I want to visualize this. We don't know. And she says inversely proportional to distance. And I don't know what condition that inversely proportional is correct. What is inversely proportional to distance? That formula is for a single charge sitting somewhere there, no? Yeah. So, Coulomb's law will be pointer option pen. Now, this is Coulomb's law. This is Coulomb's law. And what is the force experienced by a particular charge? That is electric field. So there will be only Force is Q1 Q2 by R square. Okay. Electric field is Q1 Q2 by R. It is Q1 by R square. Yes. Okay. It is some Q by R square. And voltage? Let us have this picture. Now, what were you saying about the inverse proportionality? Is distance square here? Correct. Hmm. 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 It is maximum. But how is it? Is the straight line rising, falling? That you're not saying. Oh, that you're not saying. Okay, fine. Okay, it is from this end it is rising, and from this end also it is rising. That's what you're saying. It is peak at the middle. Okay. I want to visualize this. I want to visualize this. So my need to visualize remains, and I'm able to visualize this very quickly. Why is it I'm not able to visualize that? Question is still clear. I want to come with arguments which will clearly show that that is how it is. Or if it is rising differently, it is not as a straight line. Slope may not be constant. I should be able to come to that point. I should be able to visualize this field. And through my visualization, I should be able to come up with what should be the E versus X to be expected. Then I will use a very firm mathematical procedure. What is the mathematical procedure used here mostly to do this electric field? Have you heard of Gauss law? Okay. So we'll do that. Now, I'm not able to visualize. Why am I not able to visualize? Why don't you all come a little forward? The afternoon turnout is low. You have not come back from lunch maybe. No? Okay. Why? Why am I not able to visualize? Or why am I able to visualize here? Okay. If it is like this, not single charge. Now I can visualize. No. Now I can visualize. Even if there are not single, multiple charges. So what is the problem here? What is the problem here? Madam, my question is clear to you? Which will be a straight line? That's the direction. That's it. All the lines will be like that. Why I am not able to visualize that? And my visualization should show that the electric field is highest class, Kriti was saying. You are all still interested in qualitatively explaining some relationship. And there, maybe you are right or maybe you are missing something. Right? I want you to move from the domain of guessing to the domain of visualization. Okay, so I'll try to restate the way I've understood what he's saying. He's taking some charges here. He's taking some charges here. What's your name? You are also Yash. How many Yash is there? Lot of Yash already there. Yashas. You are a very famous institute. There are charges here. There are charges here. He says the field between the two is going to be weak because they are extremes. And he has some charges here and some charges here, closer to the middle. That field is going to be stronger because the distance between the two is lower. That is his point. Okay, another qualitative argument. Why still I'm not able to visualize? Huh? Force, you can visualize force? How can you visualize force? Ah. Hmm. 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 I agree, but still there is a qualitative explanation, okay, of saying that. Why am I not able to visualize the electric? How do you visualize an electric field in terms of electric flux lines? If the flux lines are very high, density is very high, the field is very high. If the flux lines are low, the field is very low. You understand? So visualization, I've been repeatedly telling this. So that has to be in terms of flux lines. So how do I do that? Why is it that I'm able to draw it? Why is it I'm not able to draw here? Somebody almost came to this. I can draw flux lines when I'm given not individual charge, but when there are charges given like that, set of charges. When it is distributed as a volumetric charge density, I don't know what to do. I don't know what to do. You understand? That is hazing my picture. So I'll propose, let me break this into layers like this. This is some discretization. This is some discretization. Then inside this everything again is distributed. So I have to go for lumping. I have to go for lumping. I'll say what is within this box. What is within this box? This box. I'm lumping. Lumping into a positive charge. You get me? What is the advantage if I do like that? See, this is also one way of learning. There is never a single way. But to tell you that there are ways of learning that you are not thinking about. So what I'm doing, I'm discretizing the space. I'm considering every small cube as some space. And within the cube, charge is distributed. I'm integrating the charge over that cube and considering it as one charge. Correct? Then I will have finite number of charges. I will have finite number of charges. Once I have finite number of charges, I can draw a picture. Yes or no? This. These are positive charges. Here I can consider, let us say, in one slice, I can have negative charges. So what I've done? Discretized and I've lumped. Now can I draw the charge lines? Draw them. Draw them. I've just shown 3 layers. There are many such layers. Starts from every positive charge and goes into negative charge. And negative will be lower. Okay. Picture is clear now. You can draw lines here. Then line can go there. Lot of lines. Every line will pass through the center. That is the clearest answer to Kriti's question. Clearest support to Kriti's argument. Where is it in the morning, ma'am? You are not there. What's your name? Where are you from? From NIT. Huh? NIT only. You are a faculty or a professor? Okay. Go ahead, sir. Go ahead. No. Sir. No problem, sir. No problem. Well, you draw this, you have to make sure that the lines don't intersect with each other. Okay. Now you have to make sure that the lines don't intersect with each other. Firstly, already I'm not so good at drawing and with this particular tool. So what do? There are lines like this. I'm not drawing the arrow mark. Okay. Let's say this one. Now, this fellow will not stop there. Line originating. He cannot stop there. He is likely to go there and stop. Sorry. You see the example. And the fellow starts from there, will go like this and end there. So you draw these charges spaced out in your notebook. So there is enough space for you to draw the lines. So the middle two will be line. The extreme, the other two lines will go. You understand my point? Okay. So this is an idea. I will just freshly do that. So what I'm suggesting is, take this. Now you know what I'm talking of. Let us say only 3. Okay. You can draw as many as you want. So I'm only drawing 3 rows and 3 columns. And spaced out. So easiest lines. Easiest lines. Next. Okay. Madam. So here. I have drawn very minimal representative lines. Where are maximum number of lines crossing? Middle. So what have we done now? What have we done? There is certain volume. It is a one-dimensional problem, no matter. We discretized that. We discretized it. Now this is only 9. You can discretize it much more if you are willing to spend time. And when I have discretized within every discrete volume, what I have done? Represented that as one charge. Let's say 1 point charge at the center of the discrete element. Okay. This field should be very close to the actual field. This is only a discretized version. You accept everything. Sine wave, you are not drawing sine wave, MATLAB is drawing. Can MATLAB and computer give a perfect sine wave? It will be discretized. You are in the digital domain. If you don't accept discretization, there is no digital domain. By the way, what is the difference between discrete and digital? Continuous time, discrete time, digital. So what is the meaning? Continuous time means a signal which is valid for all instants of time. Discrete time means is defined only at certain instants. For example, you have sampled the voltage. The voltage itself is a continuous function, but the sampled version of the voltage is available only at t, 2t, 3t, 4t. So that is a discrete time. What happens between 2t and 3t? No, it is not available for you. Therefore, it is called V of k. It is Vk minus 1, Vk plus 1. What happens to k 1.1? No, no such thing. That is discrete in terms of time. The signal amplitude is also discretized, that becomes digital. For example, if you have a register, 16-bit register, it has to be somewhere between 0 to 2 power 16 minus 1. It can, right? And if that represents the equivalent voltage, the voltage levels are discrete. You cannot distinguish between 3 volt and 3.000001 volt with a digital meter. So when that is also, that becomes digital. Okay. So they are necessary portions. So we have discretized. Why did we do this? Discretization and lumping. Because only when the charges are given like this, we know how to visualize. Because the teacher has taught, electric field starts from positive charge and ends with negative charge. And lines don't touch each other. These are all applicable only when I can draw them as set of charges. That is why a continuously distributed charge density distribution, I have discretized it like this. Because of my ability to visualize. Clear? Now, I am very clear that Kritis is right. At the middle, it is highest. Can I also say how it will rise? Okay, this is E. I am not so much worried about the direction of the polarity. Okay, now all of us know, as Kriti said, it is highest at the middle. It is 0 here. It is 0 there. Is it linearly rise or linearly fall? It will linearly rise. You can see that from here. If you had more number of layers, you can see the lines go on increasing. I have only discretized 3 layers. You can have 5 layers, 6 layers. The first fellow will have only some number of lines. The second fellow will have literally more number of lines. Okay. So if you discretize it adequately, you will be able to see that. So I'll cross over this a little quickly because this you just have to verify that the electric field rises like this and falls like this. So from this discretization, I'm getting a picture. I'm drawing it in the continuous version. This is for me to understand. This is for me to understand. How do I do this quantitatively correctly in a way mathematician will accept? How do I do that? How do I do that? Yeah, what do you do? This is what you are having is charge density is available. Charge density is available. What you want is E. Okay. To be very clear, this is a scalar, this is a vector. This is a scalar and that is a vector. How can the two be related? Huh? Del dot D is equal to rho. Okay. Huh? Okay. What is Gauss law? Okay. So there are two people telling me two different things. Somebody is saying del dot D is equal to rho. Correct? That is one of the Maxwell's equation. And another one is saying Gauss law. Both are from that only. Now, I want to think through that. This is again not from my knowledge wherever I can jump somewhere. Right? I'm sorry, I'm going much slower than my intended to doing. Okay, if it is anywhere stretching, if it is anywhere unwanted, let me know. I will not jump into the solutions based on what I know. How is your response shaped? You have a lookup table inside. You have a lookup table inside. When a question is asked, you are comparing it with your lookup table entries. See if I am correct. And whichever is the closest entry, you are outputting from there. Is that correct? Is that right? Yes. So I'm asking, can that be processed output? My question is clear to you. Can you understand the situation, apply some logic, also use what you know, and suggest solutions? Is the approach clear to you? I can go from here to here in 1,000 ways. The ant can go in thousands of ways. But some way will have advantage, some way may not have a thing. But those are other points. But I should know that I can reach in multiple times if that is important for me to reach. So can I apply a little bit of logic? Can I apply a little bit of logic? That can come from mathematics, common sense, everywhere to do this. Am I clear? And that too I want to relate one scalar and one vector. I have to relate one scalar and one vector. So the vector has to become scalar or the scalar has to become a vector. So going by our vector calculus class, when can a scalar become a vector? Scalar will become a vector when you take grad. When you take grad phi, phi is a scalar, grad phi will be a vector. That is what happens with voltage. Voltage is a scalar. Gradient of the voltage is electric field intensity is a vector. So the grad operation takes that into that. Divergence on a vector means a scalar. These are two things. Other than that, curl keeps a vector as a vector. Okay, so these are few things. Either I have to apply a grad on this or I have to put a dot on that. Now, is that correct? Is that all? Is that all? This grad and dot are what? They are essentially differentiations. Vectorial differentiations. I need not have to do vectorial differentiation. I can do some mathematical operation on rho. I can do some mathematical operation on E. Their dimensions are different. Their dimensions are different. Does anybody here believe the dimensions are same? Their dimensions are different. So I can do something here and something there. The two should be related. You get my point? Other than del dot E or del dot D, can I do anything else on E vector to make it into a scalar? Is the question clear? There should be a reason why you are differentiating. It can be multiplication. I can do a multiplication. What kind of multiplication I should do on a vector to become a scalar? Dot product. I should do a, if I do a dot product, vector can become a scalar. Yes, no. So can I do a dot product with respect to what? Go ahead. That if I do, very nice, E vector, and if we take this as curve C, this line as curve C, sorry. To take this line as curve C, I can do this E dot dl over this curve C. That will give me what? That will give me what? Voltage between here and there. It is correct that you can do a dot product on this. E dot dl is certainly valid. The result is voltage. We need this. The result is voltage. The result is not taking you towards charge. The result is not taking you towards charge. Okay. Right. What else I can do? I can do over dl. dl is a vector or scalar? Vector. Why? Line as a direction. Next is d, a or ds. Right? ds. Is that vector or scalar? Is that vector or scalar? Huh? Is this vector or scalar? Huh? How many of you say vector? Raise your hands. ds is a vector. Raise your hands. Only 1, 2, 3. Raise clear. No fuzzy logic. This is 0. This is 1. Clearly raise. Madam, raise. Okay. Okay. How many of you say that it is vector? It's a scalar. People said scalar now. Okay, I think the question got confused. Vector. How many of you said vector? Raise your hand again. Okay, put your hands. How many of you say it is a scalar? Okay. How do I resolve whether it is a scalar or a vector? How do I resolve whether it is a scalar or a vector? How do I say surface as a direction? Force as a direction, very evident. Right? I push you like that, you fall in the direction. Right? How do I say surface as a direction or no direction? Line, does it have a direction? Line has a tangent. The tangent gives the direction. Does volume have a direction? So, dV is certainly a scalar. The question, dl is certainly a vector. The question is ds. How do you get ds? What do you mean by dx? What do you mean by dl? Very small length. That tends towards 0, not 0. Right? Delta L, which tends towards 0. What is ds or dA? Product of two, dx into dy. Right? Dx into dy. Like delta x, delta y, both tending towards 0. Dx, dy. That's a product, that's area. We know the magnitude. It has to be dx, dy. Are they scalars or vectors? X has a direction, y has a direction. I should take a vector product. It is, and they are normal to each other. They are normal to each other. And only a cross product will give me dx, dy. You understand my point? Okay. As a student, I am arguing out. I am not talking of a mathematician. I know that ds vector. I don't know vector or not. But even if it is a vector, it has a magnitude. This is equal to dx, dy. This is equal to dx, dy. And I see that this I can probably look at it dl in the x direction. This is also like a dl in the y direction. If I have to get the product of the two, it is the product of this dx and dy. It is a cross product of dx and dy. Okay. So that is what will give me a product. So shall I say like this? So it is x to y. When I rotate, it will move in the z direction. When I rotate it from x to y, the screw will move in the z direction. So this is going to be a ds vector. And therefore, this is a vector. Why is that important? Now I know the question is, can I do a dot product of E and ds? Does it have a meaning? Is my question clear? Okay. E is a vector. I asked you, how can I make it a scalar? Somebody said del dot E. Does it have a meaning? We don't know. Then what else you can do? You can do a dot product. What dot product we did? E dot dl. That's a scalar. That gave us voltage. Useful, not what we are looking for now. Then I can do E dot ds. If ds is a vector. There was a question whether ds is a vector or not. So we went into dv. It is dx, dy, dz. Volume has no direction. Surface has a normal. The surface has a normal. I take this. This is my normal. When I'm integrating current, okay, the most fundamental usage of j vector comes in j dot ds. This is your conductor. I'm current flowing in this direction. Okay, so this is your surface. Here, viewing from this side, this is your dx. Viewing from side, this is your dy. So dx to dy will give you dz in that direction. That's your ds. So that is a surface. This dx to dy is the surface area, and normal to the surface the vector. And now j vector dot this ds vector, they are aligned with each other, and therefore it becomes current. Okay, so a good place to digest is j vector dot ds vector. This gives you, this has to be over a surface. That is the conducting surface. And when it is equally distributed, normal and all that, j is constant. J comes out. So it is ds will become pi r square. Integral of dr will become the area of cross section of the conductor. So that is why you take the current density and multiply by the area of cross section and call it current. That is valid when j is constant. J is uniformly distributed, not otherwise, because it is j dot ds. If j is constant everywhere in the circle, here also, there also, then the magnitude of j comes out. So it is only ds. An integral of ds over this circle is the area of the circle, pi r square. So j into pi r square becomes your current through that. So we have digested a little bit of surface integral. Now, is there E dot ds? Does it have a meaning? Can I apply dot product of E with ds? Does it have a meaning? You said something on this. This is where Gauss law comes. This is where if I'm having, so we have to look at Gauss law. After a lot of this analysis, we are only understanding we should apply Gauss law. You understand this? But the mind that you had prior to this, when somebody just said that you can apply Gauss law, and the mind that you are all having now are different. Do you recognize this? Many of these would have come under reorganizing your knowledge. Some of them would have come in incremental direction. You would not have known how to argue that ds is a vector, whether ds is a vector or not. It would have been a gray area. Clear? Many of those layers will come there. They will improve your clarity. So now there is a reason to go for that. Now we have to see what Gauss said. You have to see what Gauss said. Okay, again is the session being useful to you? Yes, because I'm going at a much lower pace than it was intended, because all this finally you have to look at the road condition and drive. That's all that you can do, no matter what you did. Google may say something when you're leaving, but when on the road, you have to have something. So if something, you're not, you just let me know. So now there's a E.ds. Gauss has said what is E.ds. Okay. Now, Yashas, how do I do that now? This next page will come, no? I'll go to next. Since I said Gauss law, and you know Gauss law, I want one of you to come and write Gauss law. Why don't you come and write Gauss law? Anybody? How many of you are aware of Gauss law here? Just raise your hand. Hold. How many of you are aware of Gauss law? Raise your hand very clearly. Okay, 7. How many of you don't know Gauss law? Raise your hand. That is okay. And forgot, you can leave that. Huh? You don't know Gauss law. Huh? What class are you in? What are you studying now? Okay. Okay, why we have forgotten? Now he will remind us. Go. Huh? He will remind us. Take one. There's a new bottle, no? See, those who forgot, when did you study that you forgot? Tell me some year. Huh? Come. When? When was the year? 2011. You? 2009. Anybody earlier than 2009? Huh? 96. Anybody else? Huh? 96. I studied in 1990. 88 to 92 was my BE. This was in the 5th semester for us. I studied in 1990. It is impossible to remember that. But if you digest, you will know that. Okay, we'll see that. Del dot E is equal to minus rho by epsilon naught. Yeah, come. You go and write. What is Gauss? Is this correct or not? Do you recall this? Don't say that we have forgotten everything. Impossible. Even if you have finished the tea, smell of the tea will be there in the vessel. Yes or no? Come, you come. What's your name? Right. What? Tell it on the board. Tell it through the board. Use the board. Tell that. Do that. Draw that on a something you do. That has to be a record of that. Right? You have drawn a circle. You have put in 5 charges there. What do you want to tell us now? No, here, if you are considering equal, that is not 0. You have to put one more plus. Okay, then? If you put q1 plus q plus q plus q minus q, the sum is 0. That is not about Gauss law, no? Okay, go back. Anybody else? I have also brought you for a long distance there. Man. Why don't you derive what is this? See, that fellow cannot be ds. E dot ds is correct, right? Put ds, E vector, ds vector there first. And this below the surface integral, it's a double integral, no? That's a double integral, no? Integral. Surface integral. And what should be written? It's not ds. It must be maybe s or something. Eraser. Only write S there. Okay. Illustrate with a figure. This S, is it a closed surface or an open surface? S is a surface. Is it a closed or open surface? You don't have to worry about what he did. You can draw some surface S. Huh? Magnetic field. Don't jump from somewhere to somewhere. In this, whatever you have defined, E vector ds, okay, q epsilon is all okay. What is there is a surface, yes. Define a surface first. And relate that E and a surface there. What are you talking about? Write that as S. Is it closed or open? It's a closed surface, yes. Now what happens? No charge inside. Okay. There will be no electric field at the surface. Is that point clear? Yes, what is the point? Okay. The delta T you must be rho by epsilon naught must be minus not plus. That's the question yours. Okay. You can change that to plus later. Now finish the surface. Yes, it's a closed surface. And if there is no charge inside the surface, the electric field intensity, where is 0? On the surface is 0. Okay. Then is that correct to say? Only one positive is there. Right. You're not sure 100%. 99.9%? Okay, and you are saying some charge and something there. Still, where is rho coming? Okay, go back. Line integral, you remember? Raise your hand. If you remember line integral, raise your hand. Line integral, do you remember? E dot dl we did. And everybody says, you're integrating some quantity over a line. Correct? Calculus you have done, vector calculus you have done, right? You can't say you're not. Line integral, do you know? Yes or no? Raise your hand if you know line integral. பரவாயில்ல மேடம் அவன் இல்லை அங்கே ஒன்றும் போக மாட்டேன் கையில் என்னமோ மேலே பாம்பு கொத்தின மாதிரி வச்சுருக்காங்க கீழே பாம்பு கும்பு இருக்கா மேலே கை தூக்கினா இஸ் தேர் சம் ஸ்னேக் above? You raise something, it will bite you or something? As though it will give an electric shock, some high voltage wire is there, nobody's hand is rising. Even if high voltage wire is there, people will probably rise. People are building houses below high voltage line nowadays. What, Vajayanti? See? What is line integral? So if you keep saying, I don't know anything, there should be some starting point. What is integral? You have to go there. No. There's f of x dx you are going to integrate. And what is line integral? You are doing it over a line. There is a value of a function over a line. So it will start from here to here. Water bottle is there. Correct? It's here now. Have I done work on the water bottle? Let's call it W. Same height. Same H1, same H2. Have I done work on that? Same work or different? Different. Different. Different or same? Same. Why same? Why different? Force acting on this is mg. And when I'm moving it dh, I'm getting mg dh. I'm doing mg dh. So I'm starting from h1 and going to h2. I'm doing mg dh integral H1 to H2. So it is mg times H2 minus H1. Clear? This is 1. Now, I'm not taking the straight path. Same initial point and final point, but the trajectory is different. How much is the work done? Same. Okay. How do we calculate the work done now? How do we calculate the work done now? When I moved, I didn't move vertically. It is not DH, it is DL. It is DL. From here, I moved DL. And the force mg is downward. The force mg is downward. The force mg did not change. Here my DL is like this. Here my DL is like this. Here my DL is like this. The DL is like this in this direction. Here the DL is almost in the opposite direction too. Okay. But mg is always in the downward direction. Okay. So what is it I'm doing? This mg is force, F dot. That F dot DL. And F dot and DL are not in the same direction. F and DL are not aligned. But F dot DL gives me how much work has been done. You understand? Like this. It is the effective height only. There is a delta L that has a delta X and delta Y. I'm only counting the delta Y for this. That is the work done. So F dot DL I'm doing. F dot DL I'm doing from point A to point B. Okay. The end answer will be same because F dot DL, F is always mg and the downward direction, but the DL vector is changing. When it is here only, DL is in the vertical direction. Here DL is in different direction. Here the DL is in a different direction. So when I take the dot product, it will be lower. mg dot DL is lower than mg into DL magnitude. Okay, I'll get the same answer. So these are all I'm doing integration over a line. I'm doing a path. Is it now clear? This is what I said when you do E dot DL. You do E dot DL. You're going to get the voltage. We did that. That is there in the last slide. After having done that, how are you saying you don't know line integral? You get me? Line integral is clear? What is surface integral? We just discussed an example. What was the example we discussed for surface integration? Current density, J dot ds, integral over the surface is I. So you understand what is surface integral? Volume integral? Volume integral? Let us say the entire depletion layer is there. The depletion layer is like a box. There is a row everywhere. You integrate the row over the entire depletion layer. Not only this dimension, the vertical as well as this other dimension. So what you will get? Total charge. That is what? That is what? Volume integral. That is integral rho dV. Clear? Examples are clear. Line, surface, volume. Is there any connection that you are aware of between a line integral and a surface integral? Question is now clear? What is that? What is that? Are you aware of anything that relates a line integral with a surface integral? If we do our magnetics tomorrow morning, we will do that. H dot dl is B dot ds. H dot dl is B dot, that H dot dl, but there's a number another coming there. What is Green's? There is Green's, there is Gauss. So many names are coming. Maybe in the evening you can brush that up a little and see what is happening there. Okay. Sometimes you can say line. Line may be a ending point, starting point different or same. That may be a closed contour. You understand? C can be open or closed contour. If it is closed contour, what happens? It encloses an area. It encloses certain area. Okay. So, and if I do some integration over the closed contour, that is a line integration. If I do certain surface integral over that area of surface, it is a surface integral. There is some such line integral is equal to the surface integral. Okay. For example of that line integral, magnetic flux lines are closed flux line. So I take a closed contour. What is the closed contour? A magnetic flux line. How many of you have attended Samrat's lectures here? Samrat Das's lecture. You should have shown you enough magnetic flux lines. They're closed lines. Correct. And if I take that line and I do integral h dot dl over that line, what will I get? I will get the current enclosed. I will get the current enclosed. What is another way of coming up with current enclosed? If I do j dot ds. If I do j dot ds over that, I will get current enclosed. Right? So sometimes you can see one line integral and surface integral can be related. The same way, here certain surface integral and volume integral can be related. Now this is a closed surface. When this is a closed surface, it is enclosing a volume. It is enclosing a volume. Clear? Now, within the closed surface, I am having a charge density rho. For now, simplicity, let me say rho is constant, uniform charge density. So how much charge is there? How much charge is there? Rho multiplied by volume. Multiplied by volume. Clear? That is what, some 4 by 3 pi r cube or something. If it's a circle. Sphere. Clear? If it is not constant, what will you do? If the charge density is not constant within that, what will you do? You will do a volume integral with the variable rho. Clear? That is what is volume integral. What will the volume integral give you? It will give you the charge. It will give you a charge. So if I take this surface and there is rho everywhere and I do the volume integral, I am going to get charge that is enclosed inside the sphere. I am going to get charge enclosed inside the sphere. Clear? Now let us say if some charge is enclosed inside the sphere, non-zero charge, they don't cancel each other. Then will there be flux lines flowing out through that? Okay, simplicity, let me assume only positive charges are inside that. Flux lines will be going out. Okay, so as they say, the proof of the rain is in the wetness of the soil. The electric field somewhere on the surface is a proof that some charges are sitting inside. Nice payasam smell. Right? First rains after a long time, sense soil smell. There are many such indications. So if there are charges sitting inside, all are positive charge, let us say, they are all sitting inside this. So what will happen here? And there's nothing outside. Lines will be going out. Lines will be going out. If lines are going out, there is electric field intensity on the surface. Okay. So charge per unit volume is charge density. Charge per unit area, which electrical quantity has charge per unit area? Charge per unit area. E. Surface charge density is 1. E. What is the dimension of E? What is the dimension of F? F is 1 by 4 pi epsilon naught. Okay. Proportional to Q1 Q2 by R square. E. Q by R square. Q by R square. So that is relatable to E. If there is no charge at all inside, there will not be flux lines. The only exception is there may be a charge here and there may be a charge there and the surface is in between. Then there will be some electric field intensity because of that. But here electric field will be positive, here electric field will be negative, they will cancel out the surface integral. You understand? If there is positive charge sitting inside, electric field lines will be going out. If there is a negative charge inside, electric field lines will come inside. Net charge is 0 or no charge, no electric fields. So that electric field on the surface is a measure of whether charges are inside or not. So you have to do E dot ds. You understand? It is charge per unit area. That is the dimension. Q by R square. I have to do that. I have to do a surface integral. E vector and D vector, its argument is only epsilon. But Q by R square is important for you. So when I do a surface integral, what happens? Q by R square gets multiplied by area. It gives me the dimension of charge. You get me? The confusion between D and E is only in the epsilon. Focus on Q by R square. If I do a surface integration of Q by R square is multiplied by area. That is charge. So when I do a volume integration of the charge density, I will end with charge. When I do a surface integration of the electric field on the surface, I will end up with a charge again. Is that right? That is all. This is why I remember. This is not that I studied yesterday. Line integral C can be open or closed. When it is closed, there's a surface. There is a way to relate that line integral, integration of something over the line, with the integration of something else over the surface. Okay. And again, surface. When the surface is closed, it is enclosing certain volume. So certain surface integration of something over the surface can be related to the integration of something over the volume. The details you tell me tomorrow. What is Gauss law? What is Stokes law? Which is this law? My uncle's law, your father's law. I mean, I'm not deriding the scientists, but names are only names. But you have to understand the essence. The scientists themselves will be happy if you remember their principles and not their names. Okay, you get me? Now this is somebody can write Gauss law now. What is it roughly? What is it roughly? Whatever I've told, if you have understood, express that on the board. Go express that on the board. Why don't you try? The way you have to check whether you have understood is to put it down yourself. High school teachers will tell you, no, you must write. They'll say, oh, it will appear as though you have learned, but in the exam you may not be able to answer. What you should do? Why don't you write down? The next level, if you think you have understood, you have to put that down on paper and you have to prove to yourself. There is no teacher to come and tell you, hey. So define a surface, yes. Okay. And define some rho v inside. Then you do the volume integral of the rho v over the volume. That is equal to some charge. Then you do a surface integral of electric field, maybe with some scaling. You understand? That is only to distinguish between E dot ds and D dot ds. Why are we discussing all this? Why are we discussing all this? Diode, which my grandfather studied.
So inside this closed surface, the net charge is positive, and we know if any positive charge is there, electric field always comes outward. So at the boundary of this closed surface, we can see electric field is coming outwards, and mathematically we can say that we can see the dimension
So
of
the
E.
only thing is we cannot say that their field strength is equal at all the points on that. Okay, it need not be radial. You understand? Take those two qualifying factors. You get me? It all depends upon where exactly Q is sitting inside the shell. If there's only one single charge and it is right at the middle, if there's only one single charge and it is somewhat to the left, then more intensity on the left side, less intensity on the right side. You understand? It need not be radial and the strength need not be equal all over. And he's also not saying about point charge Q. Some total charge Q. There may be several point charges. Their sum is Q. Or there may be a charge distribution. If you do an integration of the volume integration of the charge distribution, that is Q. Go ahead. Yeah.
So like we can also see the dimensionally it is correct. Like electric field always directly proportional to R square. So here S we can write as pi R square. It will go here and it will become Q upon by some constant will come here. It will be pi R square epsilon naught. So by also definition we can, if we place a unit charge in electric field, we will absorb this expression. So mathematically it is correct. Like E is coming to be Q upon my R square into some constant. And by analogically we can observe like area vector always comes outward, perpendicular to the surface, and electric field will be also perpendicular. So these two will be parallel to each other, and so dot product will be this.
Okay, very good. What's your name? You're from Odisha. You're from Odisha, no?
No sir, Bihar.
Bihar. What's your name?
Rajan Singh.
Okay, thank you. See, whatever he knew, he has put up. So one way you can take two things from there is a closed surface, right? And you are looking at the charge enclosed. There are two ways to get at it. One is I will consider the volume, and I will consider the density, charge density, and integrate volume integration over that will give me Q. Another one is electric field. E vector and D vector are equivalent because D is epsilon E. Okay, I can do that E dot ds or D dot ds. I will leave that to you. Okay, that will give me again a measure of what's in inside. Clear? E is proportional to Q by R square. So if I do E dot ds over the surface, that will give me charge inside. That is a surface integration. If I do a volume integral of charge density in the volume, I will get same Q. There are two ways I can reach the same Q. So by comparing this, one integral is equal to that integral. Clear now? Yes? Why did we do this? Depletion layer. Now, I want you to do that without getting depleted. When I said depletion layer, this has come up. See, Kriti means a composition. So I'll say pointer options. I'll say eraser. Pointer options. Eraser. But I'm not able to erase. That means it's Kriti. It's now sculpted, not written on paper. Okay. So we anyway want this. Is there anything can be done on this, Yash? remove the lower ones. You can't do. Now, how do you apply that Gauss law to find out electric field density here? That is the question. Huh? Go to the next slide then. You know, in final one, you can remove this because it's not fitting in. Yeah, you go to the next slide. So I want someone to say how Gauss law can be used here. How Gauss law can be used for what? How Gauss law can be used for what? Finding out the electric field intensity in depletion layer. Okay, the depletion layer picture is clear. Where is the charge density? It is in a box. It is in a box. So what you have to do? You have to apply Gauss law. For applying Gauss law, you have to create that surface. That will not be a circle now. That will not be a sphere now. You have to create an appropriate surface. And they sometimes call this as a Gaussian surface. And with that surface, you have to apply Gauss law and you have to come up with your answer. Point is clear to you? Okay. You want me to draw a depletion line now? This much is my depletion layer. This much is this is the middle. One side are the positive charges, other side are the negative charges. The problem is clear now? Positive, negative. What is that I want to do? E as a function of x. This is 0 and we know this is also back to 0. We have drawn that tentatively, no? How did we draw that earlier? How did we draw that earlier? We had discretized the space. And in every discrete element, we are lumped or we did a volume integration of the charge and represent it as a single point charge. That is what you call lumping. If I have a wire like that, there is a distributed resistance. But I am going to represent that as a single resistance. That is what you call as lumping. So if I have two such things, this is represented as one resistance, this is represented as another resistance. That is what you call lumping. So lumping is the other way from distribution. When it is distributed, you do some kind of an integration over certain length and represent it as an equivalent. That is what is lumping. Clear? Because many times you use a term and you don't raise, you don't ask. This lumping is one. Okay. How do I get that E systematically now? Oh, some. How do I construct a Gaussian box? What is your idea now? You want to find E. E where? At an arbitrary x. At any value of x, specific value of x, E is constant. Is my point correct? That is, I can take E here, 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 here. E is the same. And I want that E. I want that E. So how should I be constructing my Gaussian surface? You have to try. If you don't try, you're not going to get anything. This Gaussian surface is going to be a box. Gaussian is going to be a box. And this dots are going to be on one side of the box. How many fourth years are here now? Just raise your hand. 3, 4, 5 of you. How many third years are here? Okay. I think third years, fourth years both have done electromagnetism, right? It is done in which semester? Fourth. You're viewing so. So I'm going to use that Gaussian law to find out E at this line. Okay. So how do I construct? Anybody done that? Huh? Want to draw come? If Yash had taken a seat some 2 roads ahead, his body weight would have been saved by half a kg today. Correct. So, but what do you do after defining dx? If you have to apply Gauss law, you have to define a Gaussian surface. "4:30 we break. No, what time we break? It's almost time to break. Oh, it's almost time. Fast. Okay. Box has 6 sides. It is a closed surface. Okay, you erase the lines you have drawn. You are very fast in doing that. If I have to do that, it will take a long time for me. No, yeah, whatever you have drawn only. Leave my points. Correct. Yes, very good. So can someone come and construct a Gaussian surface? Kriti, why don't you try? Yes, so if I have to apply Gauss law, I have to define a closed surface. And that surface is what is called Gaussian surface. Is my question not clear to anybody of you? So that Gaussian surface I want you to create so that you can apply Gauss law. And using Gauss law, you can come up with E. Or more specifically, if I want to find out E through the dots that I have drawn, what should be the Gaussian surface? Let me put it that way. Huh? Circle through which point? Huh? Okay, extend that up a little. Leave it. Go back. Let me say that is one edge. What is the speciality of this edge? E is constant along this edge. Okay. Let us say I construct a box like that. This box. Okay. This has 4. One side this side, one side that side. 6. Okay. This is a Gaussian box. Does this contain charge? Yes. Where does it contain? That strip multiplied by that. that is charge density, can be multiplied by volume. Can be multiplied by volume. How much is the volume? X multiplied by this height multiplied by the depth. That is the volume. Multiplied by rho will give you charge. Can I get electric field? Yes. Electric field at this point. Electric field at this point. Multiplied by this surface area. Multiplied by that surface area. What is that surface area? This height h multiplied by that depth. So this height and depth are common in both the cases. This height and depth are common in both the cases. So rho multiplied by x and this e. They are equal. Okay. So if I double the x, what will happen? If I am doubling my x, what will happen? This is x1, this is 2 times x1. What will happen? The charge is doubled. The charge is doubled. Therefore, the electric field is Sedra and Smith believe you are understanding all this. They are even skipping this. All the old textbooks used to have charge density. From charge, they'll go to electric field. Because charge and electric field are the most directly related. And electric field and potential are related through a line integration. Okay. So now you are getting that. So as a result of this, now if you do the Gaussian surface, otherwise there will be something you construct a Gaussian surface and do that. So if you see that if I construct a Gaussian box falling through this, that will have my maximum rho. That will have my maximum rho. That is my maximum E. If I consider a bigger box on the right hand side, rho will reduce. Negative rho comes. The total charge will reduce. And therefore E will reduce. Okay. E will rise and reduce as a linearly with respect to x. Okay. Now I want you to all formalize this at home. I have given you a lot of gaps. Okay. Nobody can teach you everything. That is not the idea. Critical gaps are being given. And I want you to be thorough. I'm not going to leave this. I'm going to revisit this at multiple times. Multiple things will get revisited at multiple times because many things are interconnected. When I'm doing magnetic field, I'll check something has happened with electric field. Okay, all are not different compartments. Science is not really different compartments. They are all interconnected. Understand? This is the quantitative method for coming up with E like this. Sir, if you're not clear, please tell me. And if you're not clear, you have to say where you're not clear. Okay. So after this, what is the voltage now across the depletion layer? What is the voltage? Huh? The area under this. It is the area under this. It is now blocking, let us say, 48 volts. It is like this. I want this fellow to block 200 volts. I want this to block 800 volts. What I will increase? How will I increase? This peak electric field. This has a safe limit. You cannot cross. You cannot cross. So what do? Base have to expand. How do you expand the base? Very nice. How do you expand the base? It must be lightly doped. It must be lightly doped. So, if I instead of having P and N, I will have P plus and N. This may be P plus and this may be N or N minus to indicate it is lightly doped. When it is lightly doped, what will happen? A lot of these fellows will go here into a small area and neutralize that. A lot of charges from the lightly doped side will go into the heavily doped side just to neutralize a small section of the heavily doped side. And therefore, this fellow will become like this. This is your E peak. But what is the consequence of light doping? The depletion layer is big. That is going to take a huge time, like crossing the Ganga bridge. Okay, which basically means the device is going to be lossy, going to be huge. Now, what happens if it lighter and lighter? What will happen when the doping is still lighter? Okay, it becomes bigger. And what happens if the light doping becomes just intrinsic? That is no doping. Then this will be almost flat. That will be, when will that be almost flat? This is P plus, this is I. This is, I stands for intrinsic. And I bring N plus. And I bring N plus. If I bring N plus, this fellow will sharply fall. This fellow will sharply fall. This is P, highly doped P, intrinsic material, highly doped N. The triangle has now become almost a rectangle. I'll come back to that. Thanks for saying this. I don't know how many of this didn't do that. This gives you maximum area. Okay, now let me restart this point. Why are these two areas lengths equal? Why are these two lengths equal? Because they are doped to the same strength. So some section X N vacates itself to nullify the charges over some section XP. If I make P heavily doped and N lightly doped, then what will happen? A larger section of N side will go and clean up a smaller section of P side. So the figure will become like this. The figure will become clear, Sriraj? N is lightly doped. That means the number of charges are low. So it has to give so much of charges over this length to neutralize P side only this much. Oh, normally I use capital N or small n. Both means N-type doping. Now N minus or N minus is used to say it is lightly doped. It is closer to intrinsic. Now capital N plus or N plus is used to say it is heavily doped. Notation. Okay. So this is where are we? Kriti slide. I should go to next, no? Yeah. So Sriraj, this is when N is lightly doped. When I still slightly dope, it is even longer. So the slope depends on the level of doping. If the slope is flat, almost no doping, close to intrinsic, it is like this. So I will rather call this as P plus because it is heavily doped. I will call this fellow as N plus. So I will have intrinsic material between heavily doped P and heavily doped N. So this depletion layer will be almost like a rectangle, trapezoid or a rectangle, quadrilateral.
This is triangle.
This is triangle.
Triangle for
Equal doping.
equal doping. Heavily doping both are heavily doping.
Heavily doping. Okay. For the same width of depletion layer, this end is heavily doped, that is heavily doped, so I in between. Just for you to compare. No. That is, I brought the two together for a comparison. For the same width, your area is higher. Consequent of lighter doping is a lower slope, reduced slope. So lower and lower doping, intrinsic means slope is 0. Don't mix things first. You get this E, correct? Area under E is your voltage. Area under E is voltage. Peak is fixed because E peak. Higher than that, the material can't take. Like air cannot take more than something. Every material cannot take more than that. Right? You don't want it to be too long. Therefore, don't make it a triangle. Take it to a rectangle. Take it to a rectangle. Rectangle's area is double the area of a triangle for the same base. The rest of that is all details. My job is to give you only the idea how that is being done, to make you look in that. You get that? This is the route for making high voltage. You will see something called PIN diode, PIN diode. That is PIN, PIN. Intrinsic. I is intrinsic material. Okay, let's stop here. Then we come back and very tiring, Vijayalakshmi. Vajayanti, sorry, very tiring, huh? All right. How many people are there in online audience? Hello. Yes. So we'll quickly recap what we had left. So this is my depletion layer. This is my depletion layer. And this is the metallurgical junction. This is the metallurgical junction. I have positive immobile charges here. I have negative immobile charges. This is symmetric because the fellows on both the sides have equal doping. So this much amount of fellows have gone over here and neutralized them. And these have gone there and neutralized them. Okay. So we discretized this and we tried to picturize the electric field, and we saw the electric field was highest at the middle. And then we did it with Gauss law and we did that is high. Okay. So now when I look at the electric field is going to look like this. The electric field is going to look like this. And the area under the electric field is the voltage it is capable of blocking. So I want it to block higher voltage. So let me take this itself as a reference and draw something. This let us say this portion is minus. This is because one of the this side is lightly doped. So more number of holes from here have gone, electrons have gone there to neutralize the holes here, or vice versa. So now the second case, this fellow will go like this. This fellow will go like that. So this means asymmetric depletion layer and longer on one side. Therefore, the area is higher. This is critical for us. This is the critical electric field. We don't want to cross that. Now, how long can I keep going? I can say I will erase this. Pointer option, eraser. Let me erase this. Let me say, here also I will erase. Okay, I'll make it even bigger. So, I'll make this fellow so long. So now, this fellow will come like this. So the area is much bigger and therefore it can block much higher. This basically means your depletion layer is very large. So let us say this is your actual PN junction. Your depletion layer, one side it may be like this, another side it may be like this. So my device has to be correspondingly very big. So the path this current will take is very long. Therefore, my losses will increase. So I can't go on doing lighter and lighter doping. So what I have understood is now, if I reduce this doping, the slope will reduce. So what is the lowest I can reduce? Undoped, intrinsic. If I do that, this fellow will come like this. This fellow will come like that. Let me do that. Now, let us say I'm here to here, I have a heavily doped. Here this is intrinsic, and again I do a lightly doped. Now this fellow will come down like this. So this is an intrinsic material. And one side is P, other side is N. Therefore, it is called pin diode. That pin is nothing like your hairpin. It is not that needle pin. This is P semiconductor, intrinsic semiconductor, N semiconductor. This can give a higher area for the same peak electric field. It can give a higher area for the electric field versus X in the depletion layer. So it can block a higher voltage. And the distance of the depletion layer will be smaller for the given one. Clear? Again, see, we are blocking a voltage, so it should be reverse biased only. Again, I don't want to get into diverse situations. See, we have not talked about so many things: open circuit, reverse and forward bias less than the cut-in voltage, greater than the cut-in voltage. I'll leave the details to you. I only want to see how you will go forward. I want you to understand PN junction. I want you to understand that the PN junction should be something like your kitchen or some other private room inside your house. Puja room cannot be kept next to your shoe stand, the entrance. There are some things which has to be inside the house, depending on your cultural position, what you want, etc. It's something like that. Let us say your cash valuable, you are having crores of money. You have to keep them, not in your veranda. That's somewhere inside, right? Roughly, I'm giving you something. And when the depletion layer is like, so you're going to have some additional things, which we will see how the characteristics can get affected. So when you want higher voltages, the first of the idea is light doping. The first of the idea is light doping. And light doping will not help beyond an extent. That is where you go for pin. Again, I am not saying there are no further ideas. I want you to think through this. That there are possibilities, this is certainly one possibility, whether there are more, etc. Okay. From charge density distribution, go to electric field, and from electric field, go to voltage. That is my request. Don't do your undergraduate electronics diverged from electromagnetism or electrostatics. You will get value only when you strictly marry electrostatics with electronic devices. By doing this, you will learn that. By applying that, you will understand this better. And from that point, try to understand what are the challenges of a power device. One important thing is to block higher voltage. That small diode you will use in your electronics lab will be small voltage. Here, you will have to block much higher voltages. What is the direction to move to handle that? The direction to move, the first of the directions is light doping, and an improvement over that is pin. Okay, that's where I'm going to stop there. And this light doping will happen in a MOSFET also. MOSFET has an anti-parallel body diode. So there also light doping is necessary for you to achieve that. This PN junction is not going to stop here. It's going to happen in multiple places. So wherever is a PN junction, you will see that the PN junction may have to block. If the PN junction may have to block, light doping may have to be necessary for it to block a significant amount of voltage. If it has to be significant voltage and the light doping is there, then the depletion layer will be big. Then that will naturally have an effect on the length of the device. Okay, by no means this is a course, but this is all to give you tap and tell you this, that. You come to here, Goa, okay, you can visit this, you can visit that. That's not about taking you there, right? So such many things like that. Because what we are doing is a 2-year MTech program. No. I stands for intrinsic. No. This is when normal doping. This line. When I go for light doping, this line becomes like this. It gives lighter, the slope will further reduce. How much light can light doping go to? Intrinsic. When it goes to intrinsic, this line will go like this. Field will behave. I don't know whether I'm understanding, but probably understanding. The question that he's asking is, we did the electric field for the depletion layer of a PN diode, where both are equally doped. How will it look like for a PAN diode? Question is clear to you? How will it look like? How will it look like? You see that the electric field is not peak at the middle. It is constant for a longer time. So what can you say about the charges? What's happening there? Where are the charges accumulated now? The charges are accumulated at the P and intrinsic border. And again I and N plus border. Okay. So the charges are something like this. So Kriti's single point of peak has now become long. There are now several lines here. The lines are equal. The electric field is high from this edge to that edge. There are no charges. See, that is why I'm saying when you have something, understand the picture in terms of charges. Okay. This is very, very misleading and intrinsic. This need not be so thick. Okay. Take this as much thinner. So the charges are here. And the charges are here. One side one polarity, another side another polarity. Equal flux density throughout. That is why electric field intensity is constant over a big window. The entire width of the intrinsic material, it is constant. So that is your requirement was to have converted the charges. For pin, you have to view the charges. Once you view, it becomes clear. Is it clear? Okay. So what next in diode? What next? There are multiple questions, but I want you to tell me what can be next in a diode. If you think logically. There are multiple things. I want one or the other. What is now clear to you? Diode, PN junction, depletion layer, charges there, and the charge density becoming electric field and electric field integrated to get voltage, and how you can increase the voltage blocking capability through light doping and through pin. This much is clear. Now, what are the natural questions that you would like to ask? Today we may go till about 5:45 or 6. At least we'll try to clear diodes. So tomorrow we have to rework and redo certain things and come up with that. Because all this we have discussed, you have done in your 3rd and 4th semester. So these are very, very essential for you. It's all electronic devices and electrostatics, right? This electrostatics, I'm going to leverage in the magnetostatics tomorrow. Those are open flux lines, it's going to be closed flux lines. Okay, clear. So we are going to do that. We'll rework our schedule and then we'll do that. What is the next question? I'll be very happy if you come up with questions. You can go to IV, but there's a huge jump there. Current? Okay, forward bias case. Okay. Then okay, I will answer this question in a slightly different way. Because you are using power diodes. See, one thing I strongly recommend is to look at data sheets. This is my suggestion to you across all the years. If you are doing some power electronics course, look at data sheet. Okay, data sheets are always useful to look at. If you are doing MTech, data sheet must be like really, it's like reading a train ticket or a flight ticket. You will see every detail, right? If I show you my train ticket, you will tell me where I'm boarding, where I'm getting down, all that, right? If I show you a flight ticket, you will be able to tell whether I booked my meal or not, right? At least that familiarity you should have with data sheet. Okay, you should do that. That's one very strong recommendation. The data sheet is what is the picture the manufacturer gives you. That is what they are willing to give you. You have to understand and make that, because it's a box internally, black box for that. And if you look at the data sheet and if you look at the power diodes, many times you will see that the diode you used in the electronics lab has only 0.7 volt drop. It will be some small variation only there, somewhere related to the IV characteristic Madam was telling. In power devices, mostly it is higher. Okay, so I will try to give some explanation for that. IV also will do this at some point. This is your I versus V of a diode. This is only when there is a junction. Only when there is a junction. Now there is a significant distance it has to cross. So there is something like it is a junction in series with resistance. A junction in series with a resistance. So internally from anode to cathode, there is a junction. There is also some significant resistance. So for resistance, what will happen? For some current like this, there will be some voltage drop. So this will be your resistive drop. So this much voltage drop for the diode, this much voltage drop for the resistance. So the result will go like this. Here. The two drops are getting added. The drops are on the horizontal direction. So this is one difference that you will have when you go to a power diode. Clear? So you can check that and see what is that, how it goes on. So this is a part of the resistance now. So now I will come to this particular portion of why there is I versus V there. Why there is a I versus V that is exponential. Okay, so you have your depletion. And if you had seen the books somewhere, there will be some kind of a charge density distribution like this and all will be given there. Okay, I would encourage you to see that. When you apply some voltage, you will start getting this kind of charge density distribution. Something like this and all will be there. Where on the two sides of the depletion layer, there will be some charge density. Okay, these pictures you can see. Like for the different conditions when it is on, off. And when the die is in the open condition, what they do is, there is something called drift current and there is something called diffusion current. They said net current is 0. So they equate the two. And that is how they bring out some of those expressions. So I'm not going into the details of the derivation of IV characteristics of the diode. Okay. So there are two things I would like to say. This looks exponential. This looks exponential, right? With a negative sign. This is the nature of the curve. Correct? So one fundamental point that I want to talk is, what is this exponential business? What is this Exponential business. Why do some quantities vary exponentially? This is exponentially in space. This is exponentially in space. What happens in your RC circuit when you short a resistor, a capacitor through a resistor? In time. So I have this. If I'm going to chart this, so what is going to be my equation? So how do I write that? Actually, you can write the KCL at that node. Okay. So what I will do normally is, I know VC is important here. I know dVC by dt. And this is going to be equal to minus VC by the same thing you will get in an RL also. You have L and you have R coming parallel to that and you're discharging it. It is going to be e power minus t upon tau. Tau is RC here, tau is L by R. Okay. So there are two things I would like to say in this case. Firstly, I want you to understand what is time constant. Now this is my VC versus time. Okay. What is time constant based on this graph? How will you show time constant on this graph? Why not 68%? Why not 69%? It is e power minus t by tau. You are saying t is equal to tau. So e power minus 1. E power minus 1 has some value. That is what you are saying. Okay. The more direct value of time constant is, if it continues here at the initial slope, that is time constant. From the initial value to final value, here it is from V0 to 0. It can be from V1 to V2. From the initial value to the final value, if it were, WERE were, continuing at the same rate, same initial rate, it will reach the final value in some time. And that time is called time constant. It is not something arbitrary I am throwing on your head, but this is something that you will know. So this I can do for RS, for RC, RL. No, exponential space, I from the exponential in time. Now, what was the other first order system we were talking? Law of cooling. d theta by dt is proportional to theta. That is really first order system. You see, dVC by dt is proportional to VC. VC is a system state. First order system has only one state. VC is a system state here. The rate of change of the state is directly proportional to the state itself. It will never go to 0. Why? As VC goes on reducing, dV by dt will reduce. So, theoretically, only at infinity it will go to 0. dV by dt is proportional to V. dx by dt is proportional to x. Is a first order system. And the proportionality constant, should it be positive or negative? Negative. Rate of cooling, temperature is coming down. Because some arbitrary x naught, the state has to come down to 0. Only then the system is stable. Okay, if dx by dt is going to be proportional to minus x. If it is plus x, what will happen? Some x naught will increase. Unexcited system. This is unexcited system. X naught will increase. If it is plus Vc by Rc, if Vc is 10 volt, it will go on increasing. That is an unstable system. So for a stable system, it should be proportional to minus Vc. Dx by dt is proportional to minus x is what is a stable system. That is what law of cooling tells you right at the beginning. Because hot object has to become only cool. It cannot get any hotter, right? Unless you supply some heat source to that. Now, what is the time? What is that proportionality? What is that proportionality? 1 upon time constant is the proportionality. 1 upon time constant is the proportionality. Is it clear? First order system means dx by dt is proportional to x. It has to be proportional to minus x for it to be stable. And the constant of proportionality is there. The reciprocal of the constant of proportionality is your time constant. So dx by dt is equal to minus x by tau. Minus x by tau. That is a clearer definition of. I said dx by dt is proportional to x. I said dx by dt is proportional to minus x. And dx by dt is equal to minus x by tau. That is the best way to express first order system. Okay. So let me write that down in a general form here. So whenever there is exponential, it means there is some first order response somewhere. In space also. So I would like you to see why that is there. Okay, some charge distribution, rho, right? Something is happening that makes it exponential in space. Okay, I would like you to examine that particular portion. Why it is coming like that. Now the next point that I am trying to tell is, we are very, very familiar with the usual current. What is the usual current? That is what you call as the drift current. That is what you call as the drift current. Who causes that current? Who causes that current? There is a potential difference. And the potential difference is between 2 points, and that is a scalar. If you connect if you draw equipotential lines, surfaces, and there is a normal to that, and the normal to that is the direction of electric field. The normal to this is the direction of the electric field, and there will be a current density proportional to E. There will be a current density proportional to E. Is it clear? Okay. So I'll write that here. J is equal to sigma E. Both are vectors. So if there is E in a conducting material, not in an insulating material, not in other kinds of material, where there is conductivity, that will lead to current density. J is equal to sigma E. J is proportional to E, and the proportionality constant is conductivity. And this is actually called Ohm's law at a point. This is Ohm's law at a point. Why is it Ohm's law at a point? This integral E vector is there, no? E vector. If I do a line integration of E vector, I am going to get V. If I do a surface integral of J vector, I will get current. Current is proportional to voltage. The proportionality constant is conductance. Ohm's law. So this is Ohm's law at a point. And what you say V is equal to IR is bulk Ohm's law, applicable for a bulk conductor. Okay. This is because of E in a conducting material with some sigma. And when it is a conducting material, there are charges. Charges are there everywhere. There is no difference in the charge density. But now what is happening is the charge densities are changing. The charge density is changing. This is very, very different from what will happen in a typical conductor. Typical conductor, lot of charges. You apply a voltage, current is going to flow. It is not that the charges are accumulating somewhere. Or if it is only like a capacitor, charge is only going to be accumulated. If the voltage across the capacitor doesn't change, there is no current through the capacitor. The capacitor's dielectric is now become an insulator. Because insulators are dielectrics. The material name is dielectric, technical name. Insulator is the function it does. The function it does is of insulation. Okay, that is what it does now. Here what is happening? Rho is changing. Here what is happening? Rho is changing. That means the density is changing. So, to the extent I can recall, when this density is changed, the earliest that we have seen is what is called as partial density of a gas. Have you studied of gases in your high school? No, air is there. What is air? Mixture of gases. Which gas is dominant? Nitrogen, some 78%. Next, oxygen, maybe about 21 something. Then others are very, very small. That is, they are mixed. I am bringing some gas, 1 meter cube of some gas at some pressure in some balloon, and I am releasing. What will happen? Huh? It will diffuse. It will? Why? Because I am releasing a very high concentration of gas here. That gas should not be hydrogen. What will happen if I release hydrogen? Explosion. Hydrogen and oxygen will be oxidation. Okay, it will be like a hydrogen bomb. You won't be there to see what happens. People are there, hydrogen fuel and all that has become important. You should become more and more aware of these things. They are doing subject to all that. Any hydrogen you deal with, you have to have zero tolerance to any leakage, not in paper, actually, because any leakage is bomb explosion. Because hydrogen combines with air, exothermic, it will become water. Water is cool, but the combination is exothermic reaction. It will explode. It will explode. So that's a side story. Really, some gas, not harmful. So what will happen to the gas? The density of the gas here is very high. So the gas will go on diffuse everywhere. Finally, to a point where it gets uniformly mixed. It gets uniformly mixed. So this is what you call as partial density. It's very high now. It will get mixed until the partial density becomes very, very low. So where there is a density is high to density being low, there is a flow. In some sense, this happens in wind also, right? Why there is breeze and all that. High pressure, low pressure, it is heavier, it moves. Okay, something is there also. So whenever you have a variation in the charge, okay, there is certain diffusion current. This is what you will call as drift. And when there is dou rho by dou x, this drives certain current. This drives certain current that is called diffusion current. Okay, that's the second aspect, that another aspect that you have to become aware of. After covering about the voltages, what I'm saying is, if you are looking at, want to derive IV, etc. for a diode, you will see exponential distributions. Why do exponents come? Exponents are always a result of first order responses. Either response in time or response in space. There is some first order dynamics in space here. That is why you are getting that. I will leave that to you. The second thing is, because there is a variation of the density, there is a diffusion current. There is a diffusion current. The diffusion current will happen only when the charge density varies with space. So you need the phenomenon of drift and diffusion for you to derive the IV equation in a diode. And what you will see in power diode is a drop much greater than that 0.65, 0.7 volt. That is what you will find. Is it fine? So I've given you the basic essentials for you to go. You can look at what is diffusion current, how do you write an equation for that, how do you come up with this. Clear? Is there any further questions on that? Okay, so let us end this with this expression on that. you will be able to see that the current through a diode, will be certain exponential function. Will be certain exponential function of what? The voltage across the diode. The voltage across the diode. That is, and the argument of an exponent has to be a dimensionless number. The argument of an exponent has to be a dimensionless number. There is e to the power 2, e to the power 3. What do you mean by e raised to the power 4 volt? So if it is a dimensionless number, Vd has to be divided by some other voltage. What is that voltage? What is that voltage? That is what is the thermal voltage. That is what is the thermal voltage. And this thermal voltage is from kT by Q, Boltzmann constant. You will have this thermal voltage. So this is a big number. This is a big number. How big is big? Let us say Vd is 0.7 volt. What is your typical Vt? 25 millivolt. 25 millivolt. So 700 by 25. How is that? 4, 28. E raised to the power 28. E raised to the power 28 is a very big number. Correct? So this is only still a number. This number has to be multiplied by a current. This number has to be multiplied by a current. And that current is what you call as Is. This is what is scale current. If you want a smaller diode, Is will be small. If you want higher current, Is will be bigger. Okay. This is, to a very good approximation, the IV relationship of a diode. I didn't derive, but I have told you how that comes in. The only place is if you put Vd is equal to 0, what is the right hand side? Is into e power 0. That means Is. Left hand side is not 0. Left hand side is not 0. So to make left hand side 0, this minus 1 will make Id is equal to 0 when Vd is 0. This minus 1 will make, but you don't worry about 1 because e raised to the power 14, e raised to the power 20 is all much bigger than 1. So you will normally ignore this. You will normally ignore this. Negligible. You will write only that. Fine. So this is something, and if there's a small change, if 600 millivolts becomes 650 millivolts, what will happen? 600 by 25. 600 by 25 is 24. E raised to the power 24. E raised to the power 24 becomes e raised to the power 26. E raised to the power 26. Big rise. 24 to 26 is small. But e raised to the power 24 to e raised to the power 26 is very big. The original e raised to the power 24 into e square. E square is to some 2.7 square. Something like 7, 8 something. There's an amplification of 8. While Vd is increasing only 600 to 650. Less than 10%. That is raising by e raised to the power 4. E raised to the power 4 is a fairly big number. Okay. This becomes an opportunity for amplification. This becomes an opportunity for amplification. That amplification is not possible here because it's a 2-terminal device. If you somehow make it into a 3-terminal device and try to influence that, amplification is possible. How can you achieve very high amplification? Somehow my signal input must be the argument of an exponential function. My signal output must be the output of an exponential function. Okay, if I do that, I can achieve a very high amplification. Is this feasible? Yes? Who is doing this? Who is doing this? BJT. This is what BJT does. In BJT, that VD will become VBE. That VD will become VBE. And this ID will approximately become IC. The small change in VBE will create a large change in IC. And VBE is between base and emitter. And IC is collector current. So small voltage between two terminals is creating a large change in the current through a third terminal. That is the beauty of a three-terminal device. Okay. This is what you are supposed to know on the first day of your class on BJT. You leverage this and go from that. Understand? You will see that I never start from a point, oh, this is BJT, the structure is like this, and therefore you start. You understand? That is not how the inventors of BJT knew them. They didn't have a BJT, but they something else and they came from, right? We somehow have to put ourselves into their shoes. That is why I never teach a buck converter or a boost converter drawing with a diagram and saying, oh, this is the converter. This switch can be on, this switch can be off. There are 4 modes of operation. And in this mode, this is the equivalent circuit. We never do that at IISc. The typical way power electronic books treat the power electronic circuit. Okay, I'm repeating it. Power electronic circuit, how you will see that, name any circuit. How will it be dealt with in a book? There will be a circuit will be given. They will say this is the circuit. Correct? Let us say quasi-resonant converter. Phase modulated resonant converter. They will give circuit. What will they say? This is the circuit. Then next part will say different modes of operation. This switch is on, that switch is off, this is on. When this is on, this happens. After that, this switch turns on. This is happens. Okay? We never do it that way. You have to do it at a level why the converter looks the way it does. Why the converter looks the way it does. Now, we'll say what is a buck and we'll say how a boost should do that. We should have done that ideally in this, but we'll do it tomorrow, doesn't matter. What I'm trying to do is I'm trying to set the base for that in the devices. It's not necessarily in converters. You understand? You understand a diode, you understand a BJT. Not entirely, at least to some extent. You always got to move from known to unknown. What do you know now? Now you know this diode characteristic. From this, you have to see whether I can create a BJT or whether I can understand a BJT characteristic. So the way I'm posing this question to you is, as I just said a few minutes back, I have these diode characteristic, I versus VDE. What is my big observation here? Small change in VD can create a large change in ID. Correct? Can I use this idea for amplification? Can I use this idea for amplification? How? The question clear to you? Huh? This is what at 10 o'clock tomorrow we'll discuss. At 10 o'clock, see what we are doing with power converters need not be only for power converters. That is for everything. I have never dealt with anything starting from this is a given. This is how it looks. Therefore, you start. If it is given, then we dig in and go on further. Ideally, that is not the way to start. Okay. We'll do that in converters later, but I am trying to build that. How you, from a diode, you can go to BJT. I don't want to say that BJT is PNP or this is NPN, and therefore this happens. You understand my point? What on the other hand I'm saying? This is that. This is the characteristic of diode. One very interesting thing, diode blocks in one direction. I agree, I'm very happy with that. Okay, conduct in one direction, it will block some voltage in the other direction. How do you block a big voltage? We just saw that. This is while it is conducting. Can I use this IV to create an amplifier? If I have to create an amplifier, what should I do? Clear? That is the pedagogical drive. That is the motivation. Why? I can understand BJT. As I said, nothing. There need not to be only one approach. But I'm certain that you have never had this approach. You have never tried this approach. So I am now encouraging you. You know a diode. From a diode, ask yourself a question. Can I use this physics behind the diode? Leverage this and create an amplifier-like device. Clear enough? When are you going to answer this? 10 o'clock tomorrow morning. That's our time. Huh? So, who is going to answer the question? Who is going to answer the question? Huh? All face going in multiple directions. Who is going to answer the question? Yash is not seeing me. You are all going to answer. That you are all doesn't mean that everybody, somebody's job, anybody's job, everybody's job. No, it could be anybody's job. So, please be prepared. Okay? See how you can do this. Deal with this. These are all known. Diode is known, BJT is known. But really to understand how with the diode you can go and create a BJT, like will make you creative. This is all what can really make you, what is the term they use every day now and then? Innovation. This is all that can really make you think in that. You have to really exercise your capabilities with that. Okay. Sorry, it was a long day. Many of you are very tired. Okay. All right.